Hello everyone, welcome to another video of this channel. This is the first of the big three bosses of 2025 Flareon. Until now it was just fine, but now the real thing starts. And look, to be honest, 7 specifically, 8 is somehow more doable and more reproducible, so as 9, but 7 is kind of different because the way it's set up and the way I solved it and many people solved it, and that is via dynamic analysis, not static analysis. Unfortunately, I'm not able to reproduce 100% exactly the exact situation that I was while actually solving it. Like while I was solving it, I was much more in an intense mode. So yeah, this feeling cannot be reproduced. So I will try. It's been quite a while actually. It's been 3 months. So I have kind of forgotten my exact one by one steps. So trust me, but most of it today will be like I'm dealing with this first time because I have forgotten a lot of details. So it will be like I'll solve it for the first time again. Of course I have my notes and the scripts and stuff, but I have forgotten a lot of details, and this challenge has a lot of details. So be patient, this video might get a bit large, so bear with me. I will try my best so you don't get asleep. Because yeah, you just listen to a guy talking randomly about reverse engineering and malware analysis, you might get bored and you might want to close this. So yeah, I cannot do anything about it. It's been clear that the purpose of these videos is to show 100% raw content, to see exactly what issues am I dealing with, so when you deal with them, have an idea of what you can do to solve them. Like you might find some of my approaches efficient, and some of them might help you, so you can use them too. Of course, I could just do some basic editing, cropping, crop the part that or fast forward the part that fast forward is actually a choice. So I could just crop the part that I'm struggling, and you boom get the solution. But it's the process of struggling. It's is the hidden element, the hidden component behind getting better. Like when you actually struggle and you solve this struggle, this is where you get better and improve. So if I crop out this part, it's like I'm cropping out the entire educational process. This is my approach. Other channels do not follow this approach, so you don't get bored. But the purpose of this video specifically, the Flareon videos, is this, the raw content. For other videos, okay, I'm doing some editing, basic editing. I'm not into much filtering and stuff, and filters, and yeah, I want to keep it raw, technical, scientific as much as possible. So yeah, unfortunately, flashbang incoming. Yeah, as I told you, it's been 3 months. It's 24th of January right now, and yeah, the Flareon website is down, so there's no way to see the description. Hopefully, hopefully they have uploaded last year's here. No, they have not. No, we don't have this. Okay, anyway, unfortunately I don't have the description right now, but trust me, it wasn't useful at all. So the challenge is called "The Boss Needs Help." Okay, I have unzipped for you, and it contains basically 2 files. You can see from here. Yeah, it's hopeanddreams.exe and packets.pcapng. I have renamed .exe to basically nothing because, as I have told you from the fifth video of the challenge, the video of the fifth challenge, in Windows work with extensions, and if you remove the exe extension, you basically cannot accidentally just double click and run it, because it might be a malware sometimes. So yeah, I have also thrown the binary into IDA, so I save some time. We will get more into it later, but first of all, there is a pcapng file. This is basically a packet capture file. This file can be opened with programs like Wireshark, where you can see the captured packets one by one. So let's do this right now. I double clicked and open with Wireshark, and you can see that the traffic, we're given this traffic basically. Okay, it's some HTTP traffic apparently, so we're dealing with some HTTP server. We will see. But why are we provided with this pcapng file and an exe file? If you played last year's Flare-on and a few other reversing challenges in general, usually when we're given a pcapng file and an exe file, this basically indicates that the traffic, the packets shown here, the traffic here, is actually produced from the exe itself. So it's like it's just like this binary is some kind of server, and we actually, when the author created the challenge for us, they ran the server, did some magic boobity, and captured the traffic and created this package for us. So let's follow the stream, the HTTP stream. The fuck happens? Follow HTTP stream. Wait, where? Oh, okay, it's on the other screen. Yeah. So, yeah, this is interesting. You can see. Okay, the first packet. Okay, I can zoom. Nice. So there is this /good endpoint being hit. There is also the user agent. Yeah, it's from Avocado OS. I don't know what the fuck is this. It looks like some custom user agent. There is also a better token. I don't know what this is right now. What it can be used for. We can also see the host and the port being used. So the server is basically this 12.flareon.com. This is 100% not standard. It really looks like Flare specific. Like 12.flareon, it indicates that it's not any random domain in the web, but it's a domain specifically created for this CTF. A potentially local one. It's not a global one. If we try to access this, 12.flareon.com, of course we get nothing. So it's a custom domain. Sorry for that. It's a custom domain that the author created to create the challenge, to run the challenge. Give me a moment to see something with the filters here. Okay. Okay. So the traffic is intercepted like this. The client accessed this server and with /good in the end. So basically, this is an HTTP server, and /good is an HTTP endpoint with a get request. It sent basically a get request to /good. So the server responded. Of course, this is the request. This is the response. You can see that the blue ones are the server packets, so the response packets. This is the client. This is the server. So the server responded with an OK response. And apparently the server is just a simple HTTP Python server, You can see that this is publicly available, and this is of course done. Yeah, I think simple HTTP is this. You know what? Maybe it is the kind of server that we open up or that we spawn when we do something like this. It's maybe it is basically, I think it's basically this. Yeah, simple HTTP it is. Let me see again. Yeah, it's simple HTTP. Yeah, I'm pretty sure this is it. Yeah. So anyway, it's a local web server used to create this challenge, and we can see that the response is JSON. So the key, it has a key of D and some hex data. We do not know what they are. Of course, they do not look like valid ASCII. If we try to view, actually, you know what? Let's work with Wireshark. In Wireshark, you can go to this list. There are a ton of options, but if you select row, you can see, sorry, not row, hex dump. Yeah, you can see the response like that. Basically, I fucked up. Sorry. Yeah, you see the alignment is perfect right now. So, oh, I cannot see the raw data. Okay. Oh, what the fuck. Okay, so let's go to raw. Let's copy, not raw, sorry, ASCII. So let's take this. You can see that these are some encrypted data. We do not get much from this. So yeah, let's just have it in mind for now. So after this /good request, there is also a post request being made with from this host. The host is the annual tradition of staring at disassembly for weeks to realize the flag was just stored with the file name the whole time. Yeah, it definitely is a custom web server. I do not think this domain exists publicly. Maybe someone has hosted it, I don't know, but I'm not sure. Oh, lol. Lol, this actually exists and is a... Okay, I didn't know that. This actually exists and is a rickroll. Okay, interesting. Someone literally created this domain. He spends money right now. He bought this domain just to host this redirection to the rickroll. Okay, why not? So, the post request contains a body, right? It contains again a D value with the message sys_i. We do not know what this is, and the server responds. Again, this and this are both encrypted. You can see that they are not valid ASCII. Basically, how can I understand if it's ASCII? I can see 51 is ASCII. Anything below 7E, anything below the value 7E, 7F basically, is considered an ASCII. So this is hex, so 51 is ASCII, 34 is ASCII, but C8 is not ASCII, A4 is not ASCII, 86 is not ASCII. So this is a proof that this is encrypted data. So let's move again. There is a GET request being made with from this domain at this port, 8080 port. Okay, so /get. The server responded with some data again. Let's move to, yeah. This is another GET request with another response here. And now it's a bit different. There is a /re endpoint being accessed with a post request. The domain is the same, of course. And now this is the body, and the server is returned sta received, STA. Okay. Another GET. another get, another RE, another get, another, and it goes on like this. This is another body, it's much larger. So if anyone is not familiar with this pattern, this is a almost clear indication that we are dealing with a malware, a C2. So what is a C2? C2 malware. Malware C2 communication. Let's see some images. So there is a C2 server, right, that communicates with an infected host. Wait, I am mixing this up again. I'm confusing this. Give me a moment. Yeah. So yeah, what basically happens is that the infected host, the infected machine, is used as a machine to execute instructions, to execute commands, any command that the malware, that the malicious actor wants. So this is basically a command. So this is basically a command. Not this, sorry. This is basically a command, right? So the server responds that it's received. Sorry, 25, 26. And here is the response. This pattern continues. This is another body, command body. So it basically remotely tells the host to execute commands for the malicious server, and the infected host executes these commands and returns the results encrypted to the server. This is exactly what happens here. So the entire traffic is done under encryption. And you know what? What's the length of this actually? This is 96. We see that this is not by chance. Okay. You can see that. Yeah. This is not a coincidence. The length of each of these D values is a multiple of 16. So I divide by 2 because this is hex, so the bytes are exactly the half of them. So this is 64 hex characters, right? So divided by 2 we get 32 bytes. 96 is also a multiple of 16. So this indicates that the traffic is probably encrypted with IAS or some other block cipher that has a block size of 128 bits or 16 bytes, in other words. This is a big indication. So if I try to compute this, this should be 96 again. Sorry, 96, yes. Okay, this should be again a multiple of 16. Yeah, I got 160. It's a multiple of 16. And goes on like that. After some time, I know because I have solved the challenge, you can see some big thing being sent here. It's received, it responds. This is another command. We go on like that. And in here you can see the big packet being sent. This is the biggest packet of all. You will see, you will understand what are these data when we're about to solve the challenge. Of course, the purpose, the task of the challenge is to decrypt the traffic and figure out what was the plaintext communication between the server and the infected host. Okay, so we can continue like that, but yeah, it's over. There are 81 streams being done. Okay, that's all. So the purpose is to understand how the malware works. Of course, it's not a real malware, it's a CTF malware, so we're not afraid. So yeah, the task is to decrypt the traffic, understand how the traffic is encrypted, then be able to decrypt it, and the flag should be hidden somewhere. So let's start with this. First of all, we start with a big problem. We can see that this is the main function. Okay, if we try and look the body of this function, we can see that it's enormous. Like, the size of this function is yeah, this is an 109 kilobyte function. This is a big, enormous, if I can say. Also, you can see there are a lot of variables. So this is something like dword PTR. These are all dword PTRs. Okay, so yeah, there are about 290 variables. So if we try, this is the function, you can see there is some obfuscation going on, a lot of OR operations, XOR operations, too much stuff. Yeah, it's a bit weird. It's not something that we are dealing with every day in an everyday function. There is some obfuscation going on here. So let's try to decompile this function, and we get the first problem. Let me reduce the sound of this because I know it's annoying. Okay, so the function, of course, is too big to decompile. So this is the first problem. We need a way to decompile this function. So let's look. IDAPython too big function. Let's leave from the images. Yeah. Okay, there is a post for this. Of course, Igor tips is the best. So we can actually go to the plugins, options, hexarrays decompiler, and increase the max function size to analyze to something like 4096, like, I don't know. So let's go ahead and do this. We go to the plugins, hexarrays decompiler, okay, analysis option 3. Yeah, here you are. So let's say change it to something like that. That's all. Let's decompile this now. It doesn't work. Maybe we should restart. No, I don't know. What happened? Should I restart? Let's go ahead and change the file. Wait, let me check. So we need hexarrays.cfg, right? Where is this file? Hexarrays.cfg. CFG means config, right? So yeah, this is the file. This is the file we want to modify. And what's the value? Max func size. Max func size. Okay, it's not changed. Oh, we need to run as admins. Okay. Okay, I think that's fine. What the fuck was this? Anyway. Okay. Let's try now. No. Okay, let's close this, save it, and reopen it. Oops, wrong. You got spoiled. It's okay. You're here to learn, so it shouldn't matter. Okay, let's go ahead. And this is the main function. Is this a main function? Yeah. So yeah, it decompiles now. It will take some time, but we will eventually see some output, something going on. Until then, since we already have trouble with decompiling and understanding more in depth what this challenge does, let's go ahead and try some dynamic analysis. So let's use, for example, API Monitor. API Monitor is, as the name implies, it's a program, a software very useful, which you can run the program of the program you want, the binary you want, and you can from here there is a list with APIs. For example, here, no, let's go to, for example, data access and storage, local file systems, directory management. You can see that there are a lot of API names, and you can check or uncheck any of them. The APIs that are checked will appear on the monitor process. The more you have checked, the more slow the executable will run. So we saw some internet traffic going on. We saw some network traffic, like we saw some packets in the Warsack, right? So it does make sense to basically uncheck everything and keep everything related to internet and connections and the network in general. So let's go ahead and do this. Let's uncheck everything. We want as less bloat as possible. So we keep anything related to web, to the internet, and networking. Yeah, networking should not be that useful. Ethernet is more than enough. So let's also keep anything related to data access and storage. And let's go ahead and run the binary. We could just rename to exe, but I won't do this. Okay, the function is still decompiling, by the way. It's enormous. Anyway, so let's go ahead and throw the binary inside. Yeah, of course. Oh shit. So what is, I should okay, I should really stop having these bars, these tabs open. This is annoying. Anyway, it cannot execute because it needs an extension .exe. This is stupid, but anyway, let's rename to exe for now. Okay, the function is still decompiling. Yeah, so yeah, let's rename to exe and run it. Okay, for some reason it didn't capture anything. Like it literally exited. The heck? I'm not sure about this actually. The fuck? Okay, you know what? Let's disable the filter. Oh, there was some filter. Okay. So okay. Okay, let's throw everything away and run it again to see what happens exactly. Let's throw this away and wait, let me, yeah, and yeah. So interesting enough, we see that it calls get other info to this domain and this port, so it actually tries to communicate with this port, try to open a socket, but of course this domain does not exist at this port. No web server is running at this host and this port, so it throws an error. You can see that the response is WSA host not found. So of course, since it does not connect, it does not proceed with the rest challenge, and it just exits. Okay, so no luck here. We need somehow to create this host locally, so we are able to interact with the binary. Otherwise it will be extremely hard to deal with. Okay, this is getting annoying. My PC is a toast fryer, seriously, but I did not expect it that much anyway. So there are a couple of solutions here. So our task is to be able to communicate with this host that does not exist. Of course, we're not going to go and buy this domain, like go to a domain hoster and buy this domain, because we can host this domain locally and may actually point it to our local host. So we can go to our hosts file, to a local file that is called hosts. In Linux is /etc/hosts, and you actually tell them that, okay, I want to map this domain to my local host. So when it actually tries to communicate with this domain, behind the scenes, it actually replaces this with localhost and instead tries to access localhost. Right? So this is what we're going to do, but the other solution is to use the Mandiant Flare, how it's called, fake DNS. Yeah, fake net and G. So this is a suite. Yeah, it has a lot of tools. One can basically take a look here. You can do a lot of things. You can create a custom fake web servers, fake domains, fake TCP. You can create listeners, yeah, anything, diverters. There's a lot going on here. So I really have never used this tool because I am always okay with the solutions with the hosts file. But you can give it a try, I suppose. You can do a lot of things with this. Also, I have talked with other players and many of them have used this to solve other challenges. The heck is this? Okay. Yeah. There are quite a few dependencies. Maybe this is why I have never tried it. I'm bored of installing so many dependencies, and who the heck uses a VM? Okay, the function is still decompiling. So yeah, you can, the most important use case is that you can redirect all traffic from this IP right to this. You can make everything. Anyway, HTTP, DNS listener, row listener. So basically for our challenge we would need a DNS listener. Anyway, let's go ahead and create this. So you can find this file in Windows System32. So yeah, let me show you. Windows System32. Let's remove the flashbang behind. It's still decompiling. Fuck this shit. Drivers, etc, hosts. So this is the file. Okay, this is some stuff from Revi OS because I'm not using a standard Windows installation. So 12.flareon.com. I cannot save it as is, I need to be admin. So yeah, what we did now is that when it tries to access this domain, it will basically look at the hosts file and check what IP does this domain map to. This is our local host, so we're good to go. And now okay, let's go ahead and remove this and try to run it again. Of course, we added it, but nothing changed yet. Nothing changed, of course. Okay, actually it did connect now. Yeah, of course it did connect. But there is a problem. There is another problem here. Look at this. It tried to connect to it, like get other info worked, because it found out that look, 12flareon.com exists, but then it tried connecting to it at that port and it did not work, because of course we're not listening to that port. So if I try to ping, look at this, you can see that we are mentioning this domain at our hosts file. So a ping request, so this ping basically corresponds to this, and of course this is always instant, like communicating with your local host is always instant. So these two are equivalent. Now what about connecting to it at port 8000? Let's try to connect to it at port 8000. Sorry, it's not NC in Windows, it's netcat. And we can see that it does not connect. But what if, let's open another terminal, and you see no connection could be made, like, right? So let's actually listen on this port, and let's have some verbose as well. So we are listening on this port, and now let's try to connect to it from the other terminal. We can see that we connected to it successfully, and we send something here. Okay, why we don't get the response here? Oh yeah, I click enter and it refreshed. So we see this connection and the message that we sent. Yeah, it needs some refreshing. I have to enter. Okay. Oh, if I type something in the server, you can see that it responds here. This is basically TCP communication. Okay, this is a typical TCP socket. No HTTP is involved. It's just raw TCP. Okay. But as we said, the challenge works with HTTP. So let's go ahead and see what happens with this. Let's go ahead and listen to this port again. And now we will run again the binary again. If we run the binary, so a non-blocking, what? A non-blocking operation could not be completed. Oh, send was called now. Oh, you see send / good. It worked. Oh yeah, we saw the connection, right? You see that? So what does this mean is that the binary that we're provided is basically the client, and it sends a request to the server, which is hosted here, but our web server is just a plain TCP socket. There is no handler that says that, okay, when you receive this request, you respond with the specific body. We did not did anything like that. Okay, so what happens now? What I'm about to do is not what I did in the challenge back then, but it's important to understand. I actually spent a lot of time here because I was not very familiar back then with this concept. But when an HTTP request is made, it really is not a good idea to respond with plain TCP. Like I could respond here, like I could respond with that, okay, and you'd see that it received some data, but of course it exited because, of course, this data did not have the correct format. If you remember, it expects the returned data to be valid JSON. So let's go ahead and try that. I'm really not sure. Okay, we received the connection. The bearer is the same as we saw in Wireshark, if you remember. So let's send the valid JSON actually. Like 1, 2, 3, 4. It did receive the data, but it still exited. So now it's a bit black box that what we have to do. That's a bit unfair over here. So the function will never decompile. I will stop this right now. I don't want to tire my PC more. But let's go ahead and sort the functions by their length. We can see that the main function is quite large. So let's go on a bit smaller function like that, or like that. I should not like that, do that. We want a function that has similar structure. Yeah, so this kinda looks the same as our main. So a lot of constants, a lot of XORs, adds, subs. So let's go to this one, for example. Yeah, anything, not this, this, and decompile this one instead. This will take much less time. Yeah, so let's go back to this. So we need a proper way to set up an HTTP server locally. This is what we have to do now. We need to set up a local HTTP server. Let me turn this down a bit. Okay, we need to set up a local HTTP server and properly respond to this request, because responding like that is not doable in HTTP requests. When we responded like that, we basically responded via TCP. This is a plain string, but the HTTP, there is an HTTP, how can I say that? In this binary, there is an HTTP formatter, I can say an HTTP, there are some functions from external libraries that craft and set up an HTTP request from scratch, like adding all the CR/LF/R/N bytes, and they craft anything from scratch. And when they get the response, they parse actually the response. So they expect it to be in a proper format. We cannot send any data that we want. They must be valid HTTP response data. Okay. So we basically need an HTTP server. This is not an HTTP server, this is a TCP server that we opened. A raw TCP socket server that we opened. We need an HTTP. So you can do many things here. For example, you can do something like that. And okay, I'm gonna cheat here a little because I remember there is a very good simple HTTP server that always worked for me. Yeah, and it is basically this one, exactly. This is basically it. Okay, but now that I think about it, let me open an HTTP server on this port, and let's run the binary and let it connect to it. You see that it actually accessed /good, and it received some data back. It received the response, but we need a custom response because, as you remember in the Wireshark, it's a JSON string being returned. So this is why it crashed now. This still takes time. Okay, so I don't know this orange shit. Okay, so this does not work as well. So what are we going to use basically is this script, this simple HTTP server. I don't like this orange thing popping up. Can I just remove it, please? Anyway, don't give a shit. The heck is going on? Anyway, okay, so I will sit here a little and go back to the server and take this because I have already decompiled. Fuck yeah. So this is the function that you showed earlier. The decompilation is huge and you can see that it's very obfuscated. This is the entire thing. Okay, we can throw this function in an LLM, but even if I do it, it will tell me that this is basically MBA obfuscation. It's called MBA, Mixed Boolean Arithmetic Obfuscation. So look at this. What MBA basically does is basically you replace standard operations such as addition with, for example, this statement. If one calculates a XOR b plus 2 multiplied with a and b, logical end, this is basically addition. So what the MBA obfuscator does is that it replaces standard operations, arithmetic operations, with mixed Boolean arithmetic basically. So take a look at this. The addition is literally replaced with this thing. This is very hard to deal with. It's very hard to understand what operation is behind this statement, but essentially when you deobfuscate it, you just get x plus y, sorry. So this is basically what happens here. There are a lot of XORs, a lot of nots, a lot of subtractions, a lot of subtractions, additions, logical ORs, but at the end of the day, this function does something and it returns something like that. So yeah. Yeah, no, I don't want to spend the time again. Okay. Why the fuck anyway? Okay. Versions of IDA after IDA 9.0 have a very cool plugin. Actually, after 8.3, 8.5 have a very useful plugin known as Goomba. Goomba is basically an embedded MBA deobfuscator. So for example, I can select all this region and select deobfuscate arithmetic expressions, and hopefully, I don't know if it will work. Honestly, it has never worked for me. But I've seen some guys using it and it does some crazy stuff. It has very good results. It's actually one of the best MBA deobfuscators right now in the wild. So let's wait a while. It might crash. I warn you. It might crash, and it will probably crash because look at how many variables are there, so we expect it to crash. Anyway, back to our problem until this is done. So let's go ahead and open. We have the server.py. Let's open this up. So this is basically a simple HTTP server based on this. Okay, my PC is dying. So you can see that this is a basic HTTP server based on this online and this open source server. So I have modified that on the GET requests, when the path is not, so this is the endpoint, right? When the endpoint is not /good, oh shit, this is spoil. Let's take this basically. Okay. Okay. If the endpoint is not /good, then it throws an error. Okay, so let's go ahead and basically run the server at the port 8000. It needs subcipher? No, we don't need this right now. Fuck this. Okay, so we run the server. No, let's go to the to here, and okay, we don't need this anymore. Let's go ahead and run the binary again. Throw an error. Apparently a bytes-like object is required. Okay, so it expects a byte string. Okay, apparently this crashed. No? Yeah, it did. So let me rerun this. Okay, let's run this again. Shutdown. Okay, get good. We don't know if this helped at all, but we really do not have any clue if this worked, because okay, it just received some data, but we don't know what happened after that. So we need to investigate more. This is as far as we can get. Okay. Yeah, you can see that I have exactly the same headers as I have back in as we saw in Wireshark, because in Wireshark you remember that there was this server, this date specifically, and I tell it that the content type is application JSON. It's a JSON object. It's a JSON string being written to the response body. Actually, what happens if I just send the raw data? I really don't know. I'm just practicing. I'm just checking how this works. I haven't tried this before. I'm experimenting as well. Yeah, I haven't the same thing. Nothing changed. Yeah, let me change it as it was before. Okay. So really nothing changed. Some data was received. You can see here some data was received, but you know what? Let's replicate the exact same traffic. So let's replicate the exact same steps. It started with responding with this thing, and it then sent this string. Okay. So let's respond with this. So let's go ahead and try this again. We really don't know. It just exited. It received this, but it did nothing with it. So we're not really sure what happens. Okay. Give me a moment. Where is it? Follow TCP stream. Not this one, but this one. Okay. Let's take the entire thing and JSON.dump_s.encode and this entire thing. Okay. Okay. This thing is still being deobfuscated. It takes a lot of time. No luck here. Okay. Yeah, we don't really have any idea why this exits. So we need to investigate. And by that I mean that we need to see what happens at the after receive function. WSA poll is runs and close socket is called here. So let's go here and try. No. Let's go to the rec function and see where it's called. It's called at one place only. It's called at this method. You see, this is where the receive happens. This is the method. This function, where is the red? It's yeah. You see that. Look at this address. 2C24. 2C24. This is exactly the next line after receive. So this is the call stack. It is called here, and this method was called from this event method. So it's 54fd. 54fd. So this is the call. 54fd. So let's rename it to something like calls receive, right? And yeah, this is basically it. Okay. If it's larger than that, it exits, does some calculations. This came from 3735. The heck is this? 3735. This is it. This could be it. 3735. Oh yeah, this is it. So 3735 is this method, and yeah, this is the indirect call being happening. So this comes from the call to this method, not this, sorry. The call to this method that calls receive. You see that this function has no X references. Yeah, that's because the call to this function is being done with an indirect way. So it's evaluated at the runtime and called at the runtime. Okay. So let's go ahead and actually debug this program, because we need to understand why shutdown is called. And basically, you know what, we can identify it like that. We can go ahead and find out where shutdown is called and work our way back. So shutdown is called at 8211, so that would be this. Yeah. So you can see shutdown and then immediately close socket being called. This is the exact same way these functions are called. You can see shutdown and then close socket. Okay, and yeah, so this is the last method being called. It terminates. Connection established. Okay. We are already deep into the challenge. It's too late to regret this right now. So this is the method, nothing from here. I don't really understand. So this is D780A81, what? D780A, okay. D780A, no, this is it. 80A. Really? This does not really help. Okay. Yeah, this is apparently wrong. We need to go here. Yeah, this is it. D780A. Okay, okay. This is where it's called, of course. And what about this? What's that? 74FD. Oh, it's again an indirect call. Fuck this. It's an indirect call. This is bad. Okay, and then shut down again. Yes. So let's actually debug this and maybe find out what really happens under the hood. Yeah. So yeah, let's go and do this. So let's throw the binary into the debugger. We don't need this anymore. Actually, let's keep it open. Yeah, let's keep it open as well. Okay, let's set up the server as well. What? Oh, yeah. Don't mind about this right now. We just need the placeholder, the boilerplate code for the HTTP server, just to have something to run. This could probably also work by doing this, by having an HTTP server set up like that. But then, if we get a response, we cannot create a manual response and say, hey, you will reply with a JSON string. So we cannot actually respond with a JSON string with that way. If we set up the HTTP server like that, then we're able to have manual responses. So here you can see that we respond manually. We respond with a code of 200, and we can respond with custom headers and stuff. And this is the actual body. We cannot do this with this Python server, this simple Python HTTP server. Okay. All right. So okay. Okay, let's go ahead and go to shutdown. Let's run this. So it stopped at main, nothing really interesting, and it just called shutdown. Why though? Let's try to understand why. Yeah, we saw that this is the indirect call. Okay, what's that? Send request wrapper. Actually, you know what? Let's try and pull some symbol from Lumina server. It did not work. It did not work. I don't know why. Anyway, we need to understand why this happens. Oh shit! I have left some symbols from the time that I solved this challenge. Anyway, I think it's gonna be fine. Oh shit! I have left some comments as well. Yeah, I have some comments, fuck. Anyway, it's gonna be fine. So, let's go ahead and see why shutdown was called. So it was called here. So it has to do with this call. Okay, you know what? Let's breakpoint at receive so we know what data were received actually. Let's run it again. And we don't need this, and let's run it. Yeah, we have a breakpoint at main. Why? Let me see something. Is there any TLS callback? Any useful TLS callback? No. Never mind. Okay. So let's go to the debugger again. And let's run this. So it receives, okay. So let's go at the end of receive, and we can see that this is the response, the HTTP response. Let's grab this and open it in a more suitable viewer. I think it's Control E. Yeah. No? How can I see this data? Shit. How can I do it, please? How can I do it? Display type. No. Okay, so it's Control E apparently. Okay, I can go here and show you. Okay, I copy pasted the thing from x64dbg, and you can see that this is the response done by my custom HTTP server. So it really responded with the body that I asked it to respond with. So it really responded with this. It really added server date content type. Okay, for some reason it added date twice. Okay, it makes sense. It adds it by default, so I think we don't need this. Anyway, so server and content type. And JSON. Okay. And response with OK. That's fine. Until now. So let's run this, and yeah, this probably works, I suppose. So it calls mem copy. Let's debug a bit of that. Hopefully will make some sense. Okay, very interesting. Can you see that? At this point, it compares R14 with D, the D byte. And if it's not equal, let me show you. Wait, what? It really did what? I think it literally crashed when trying to parse the HTTP response, because it was actually this /d. Can you see this 0D byte? This is basically this is /r, and the HTTP requests and responses are basically separated. The separator is /r/n. So this is a strong indicator that this function is basically the HTTP response parser. This function parses the HTTP response and checks if it's valid. So let's search for this string in IDA. We press Alt and B, and we search for this sequence, and we find the method. This is it. So it expects so if R14 is not 0D, it jumps here, and then it jumps here, and does some stuff. Okay, why it crashed now? Oh, I see why. Oh my god. Fuck. No. This fucking potato PC. I will never change it. I will always leave it as is. Never buy something better, never. So this is basically a method responsible for doing some HTTP related stuff. Okay, so where is this method called from? This method is called from 6bfc. So 6bfc. Oh, you can see that this is a method 6b60. So 6bfc, this is where so this is basically does some HTTP checks, right? So you can see that this we are inside the code that does the HTTP parsing. You can see that this is some regex here, and it checks if the response starts with these bytes, HTTP /1.1 or 1.0, 1.1. Then it expects a 3-digit number. /d curly braces 3 means that it expects a number with 3 digits. This is the response code, 200 in our case, and then anything and /r/n in the end. Okay, so let's go to the end of this function and check the response. It responds with 1. This is good because it means that we get into this section. Is it true? No, it should not get here. What's that? What's that? Okay. I'm not really sure what this code does. It's a bit weird. Anyway, let's get inside. Does some shit. Okay. And this should be a mem copy, I believe. What's that? This looks like a weird constant. What's that? Nothing. Anyway, this I think this is okay. Let me check. Yeah, this is a string copy function basically. You can see that the first argument, so this is basically written at this point with v7, and v7 is v6, and v6 is that. So yeah, this really looks like a string copy function. So if I understand correctly, oh yeah, and this is the regex string. So this is the regex string. This is the regex string. All right. So we want to get into this method. This is the important thing. So let's go then there. Let's keep this for now. We don't need it. And yeah, skip all that stuff. This is a loop. Oh, so yeah, it's pretty clear. It parses the first line basically. You can see it parses http /1.0 200 OK /r/n, and that's all. It parses the first line. So RDX has the length of this line, and that would be 11 in hex, so 17. So this is 17 bytes. This is 15 plus /r 16 plus /n 17, so 17 in total. And oh, it adds RCX. Oh, okay, so it skips the first line. So it just skips the first line and moves on to the second one. Okay, interesting. So first line length this is the response, right? And this is we can say that this is a char asterisk. Okay, first line length, let's make everything capital to be clear. I like capitals before because it's clear. So it moves to the second line and it checks the server apparently. Okay, it's trash, it does a lot of things. We most probably do not care about this method at all. We can simply skip it. Probably it's just gonna return 1. Yeah, it returns 1, so we don't care about it. So let's go below all of this. This is a mem copy, and yeah, what's that? F0 F0. What's that? We do not care also about this. Okay, cool. So this is a mem copy again. What's that? 1670. So what's that? Oh, okay. This parses the response code. So parse response code, right? So this returns C8. If we go to Python and convert the C8 decimal, we can see that it's 200. So this function, not parse, extract response code, response status, if I might say, extract return status. Okay, this is clear. And this is the response. Okay. Okay, here it checks the response status. Okay. Alright, string clear. It's over. Most likely we are losing our time here. We're wasting our time, but never mind. So it mem copies. It copies the OK, F0, F0, we don't care about this, jumps, oh, what's that? Okay, it checks if the response is 100, but no, the response is 12, it's 200, not 100. Anyway, it goes to this branch, basically skips everything. Immediately calls this, it's useless function, and it basically exits. Okay, and checks the response. Oh, nice. Okay, the response is 1, so I think it succeeded. Alright, where is this method called? It's called here. Okay, it succeeded, so we're good to go. Okay, that's good. That's good. And here it checks the request. Okay. Okay. So let me check something. So let's go to this method. What's this? 2ab0. Yeah. Okay. So what's RCX here? Okay. I think we can skip this method. Okay, so so this is parse response line, parse remaining response, if I might say. This is what this method does. So okay, you can see that we skipped this function entirely, and it populated with this string, which is basically the remaining response apart from the first line. Okay, so it returns 1, which means it's valid. It's a valid HTTP response. It checks if R8 is 2, but no, it's 24. 24 is 36. Is this? Yeah, this is the length of the next line. So this is 34 plus 2, 36. This should be fine. It compares. If it's okay. Wait, this value is large. Lol. Anyway. Oh, if it's above that, then it throws an error. Okay. It checks RBX. RBX is 0 for some reason. No problem. Okay, this is literally standard HTTP response parser. Not much to see here. All of this works by the book. Yeah, apparently. Okay. more debugging, more debugging, more of this, more of that. This is the length of the next line, which is 25, 37, yeah, 35 plus 2, 37, and goes on. It goes on like this. We need to run this. Oh no, we basically need to run this until we get to the response body, because right now it parses it just parses the headers. So we're looking for an empty line. Okay, let's check what's going on. This is a loop checking the headers, basically, nothing much. To AB0, yeah. So this is the remaining. This, so it checks the content type. Again, nothing interesting. It's a bit weird. Let's rename this extract remaining parse remaining response. I cannot find a more proper name right now. So we're almost 1 hour and a half into the challenge and we still haven't identified anything useful. This is very, very terrifying. Okay, I love it. So if challenge 7 is gone, then 8 and 9 are more doable to do in a video. 7 is pretty much a bit tiring to watch, exhausting. It certainly is a better experience in a textual form, by reading a textual walkthrough of 7, not a video. Anyway, it keeps on parsing and parsing and parsing. Okay, and we're finally over. It checks the length. Oh, now I understand why it's a 2. Okay, if it's a 2, it means that this is an empty line containing only /r/n. So if it's 2, it means that the headers are over. The headers, the header section is it's completed. So okay, so you can see here that now R8 is 2 and it checks if it's a /d. It is a /d indeed, so it basically checks this line. You can see that CRLF is /r/n basically, so it checks /r/n and it moves on from here. It calls that. Okay. I forgot to mention that I remember that when I was solving the challenge, I looked for the code that basically constructed all of these HTTP request headers. For example, where was this good string constructed? Where was this bearer token constructed? Where was this string constructed? And it looks like there was an encryption function involving just XOR. It literally was just a XOR function that decrypted the strings and appended them to the headers, to the request headers. But yes, and you can understand this because if you open the strings, then you will not find good, for example, or bearer. Oh, you can find bearer, but not the rest. Okay, this is better. Yeah, you can see that these are the encrypted strings that are eventually decrypted with XOR and used in the application. For example, if we check this, maybe I was wrong. Let's check this. Why it takes so much time? I think that's a large function. Shit. 4BA7. Interesting. So this is again an obfuscated function. Apparently, you can see that these encrypted strings being decrypted are part of one of these functions that are basically MBA-obfuscated. So we don't have any luck here. We cannot do anything. You can see that it's obfuscated, and the size of it is enormous, so it will take a lot of time to decompile, but we can give it a try in any case. Anyway, let's go back to debugging. Yeah, so this is how these strings are produced. I will not get into this rabbit hole right now because it will take a lot of debugging and you will miss the fun part. So this is a different function than the others. I don't know what it does. Let's go content length. What's content length? Okay. So this is where a more experienced reverse engineer than me, of course, would have used something like trace. So they could trace basically this part of the response and see at which parts of the program it was actually accessed. But I'm not going to do this right now. You can basically see that there is a str decrypt method here that involves a really simple decryption thing that involves XOR and some multiplication and stuff. But let's see what this is exactly. So it copies content length. Okay, interesting. Oh, it did not. Oh, okay, this was done quickly enough. Where are these XMM words being decrypted? Oh yeah, here it is. So you can see these XMM words. This is actually the decryption part, and you see that this is where the first, yeah, this is exactly the decryption actually. This entire method, it's a big it's garbage. It's all of this is literally garbage. Some people that I talked with literally were able, I don't know how exactly, but they were able to decompile, to deobfuscate all of this and just end up with this single loop that is basically the only efficient body of this method. The rest is all garbage. This is only the efficient, effective content. And this is basically the decryption loop. You can see that A1 is the encrypted text, the ciphertext. V3 is the offset, and it's XORed. Then anyway, the decryption loop is just like that. In any other case, it's A1 is simply the XOR of these values, and you get the idea anyway. Actually, what the fuck is this? It will take a century again. Hope not. Oh my god. I just got a flashback at how much is still left, and I am really afraid of that. Anyway, I'm already into the rabbit hole. Okay, RDX. So this is weird. Anyway, str decrypt is called, and these values produced. Don't remember what is this exactly. What's that? I'm not sure what this is. Let's keep it. So it compares the response with 130. What's that? Oh, it checks the response code. Okay. What's that? Skip it. Okay, 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 okay. Okay, can we find the fucking... Where is the... Let's search for this string. No, let's go to the memory map, Control B, and search for this. Okay, we found this. Let's actually hit a breakpoint at this thing. So we set a hardware breakpoint here and press F9. So we pressed F9 and we can see that we ended up inside a DLL. Of course, we don't want a DLL. This is mmove, so we want this line, memcopy. Okay, so I want to get out of this, and yeah, this is basically the contents. So apparently it passed all the checks. Okay, interesting. It passed all the checks. Okay, okay. Let's see what this does. I think this is some xbad function call. What's this? What's that? Not sure. Oh, it does receive again. Why? Okay, suppose it just receives what? Okay, nothing to receive. What happens now? Oh, it looks like it will exit now. Oops. Why? Why? What happened? I didn't understand what happened. It just received and closes now? What the fuck is this? Oh my god, it's way harder. This video is way harder than I expected. Oh my god. I don't know why I renamed it like that. It's str decrypt. I don't even remember why. Anyway, connection. Okay, connection. It reads the response all over again. The heck? Connection established. Oh, it says connection established. It's a good thing. No? It is. Oh, it shuts down. What? What the heck? Let's rerun this. Something very bad happened. Let's go to the end of this shit and basically put a breakpoint at this point here. Let's put a breakpoint here and run, let it run. Of course, it stopped inside the DLL. We want to get out of the DLL, and this is out of the DLL, and we breakpoint, and very nice. Okay, so it was memcopy, which means that the output, the thing, it was copied to RCX. Let's actually search for these bytes to our IDA. No. Let's for this is memcopy. Okay, so I don't remember the syntax. Source, destination is the first argument. Okay, it's the first argument, so it's basically how does this work? It's RDX, so RDX is the no, it's RSI. Oh, no, it's not RSI. What's the 311? Oh, this is the length of the response body. Oh, it's the length of the response body. Okay. Okay. So let's rerun this again. I'm not sure what happened. Okay, there is this method being called here, but I'm not really sure. Let's look for this. This is the method. What does it do? So what's RDX? RDX is the response body. Okay. Is this a JSON validator? I remember there was a JSON validator. I really believe so. It is. Oh. What the fuck is this again? Okay, it returned success. Apparently. Okay, this is where something happens, something weird happens. No, fuck this. Something weird happens, yeah. Wait, okay, to CD0. Oh. Okay, interesting. This is very interesting, and I get some flashbacks right now. WSA poll, what's that? I don't remember. WSA poll. An array of some poll at this and wait behavior. Does not seem very useful. Oh, it returns. Wow. Wow. This is receive, okay. This is bad. This is bad. Oh my god, this might take a while to figure out. I think that I honestly don't understand. Okay, let's no what else can I do? Let's open a light. Okay. I don't get this. I really don't get this. This is valid JSON. I don't know what's wrong. I don't know. Okay, I want to check something. I want to change this response to something that is not to something that it's not is not valid JSON, like this. This is not valid JSON, right? So let's use this. Let's run this again and check if the same happens. Oh, of course, we need to run the server. You see fatal exit. It means that it could not connect. So we'll try again. Okay, it just goes to receive. It goes to something weird happens. So until here there is no, you can see that until here there is no validation of the JSON. If there was JSON validation, then this would throw, it would have thrown an error until now. So we get into this method. All right, to see the 0. It responded with 1. Okay, this is good. And it goes to receive again. Okay, of course, receive now returned nothing because there is nothing much more to receive. So if we run it, if we let it run, it will just shut down. If we let it close. Oh, what? Valid JSON? Validate JSON? No, this is spoiled. Wait, what? Shutdown was called and then it did not exit. Why did I assume that it exits? It does not exit. It just calls shutdown and close socket, but it does not exit. Like there is an error. There is not error. You can see that it calls shutdown, it calls close socket, but it does not exit the program nowhere. Why did they assume that? You should correct me. I'm checking. Let's now close this and run this again with the correct body. So yeah, I should not, oh my god, too many breakpoints, fuck. These are all from the time that I solved this function, this challenge. Okay, let's go to receive, and that's cool. So let's create a hardware breakpoint at this specific place. So let's run this. Get out of this DLL. Cool. Then what's this? It's 78E3. Okay, so apparently we want also to set a breakpoint here. Okay, and something weird happens. No, it's not something weird. It just tries to receive more data, but no more data exists, so it shuts down. And this is the interesting stuff. Why did it breakpoint here? Okay, this is 96 EA64. What's that? 9668. What the fuck is this string? Okay. Get. Okay. Apparently this is nothing. Okay. Okay, this breakpoint is actually a bit troublesome. It just exited. Nice. Okay, I don't know what the fuck is wrong. Let's run this again. I see. Let's put a breakpoint just before it exits, so we know why it exited. Let's run this. What's that? No, we don't need this. Yeah, actually, let's put a breakpoint to all of the hardware breakpoint to all of these operations. Yeah, so here. So let's put a breakpoint here. Yeah, here and here. Yeah. Okay, let's run this. So the hardware breakpoint hit, and it hit inside the DLL. It's memcopy again, one more time. Okay, I see. What's the content we sent? Okay. No. RDI, it's the null byte? No. So it's C380. Does it have a breakpoint? No, it doesn't. Let's put a breakpoint. Not here. Follow this and put a breakpoint here. Let it run. It receives again. It does not have anything to receive though, and it shuts down. And then again inside the DLL. The fuck is this string? It's very weird. Where did this string came from? Okay. Weird. Let's remember the issue. Okay. Oh, hardware breakpoint. Okay. Interesting. Okay. Okay. I like that. What's that? This is the contents of the. Okay. Compare EAX with A. Okay, this is the. It checks the new line, alright. And it checks EAX with EF. No, it's not EF, of course. Decrypts. So I think that now we are inside the JSON validator code. This really looks like JSON validation. Because there are, oh, what? My name, my PC name. Actually, there are a lot of things happening with the JSON, so I assume that this is some sort of JSON validation happening. What? Okay, let's skip this for now. Okay, this is my PC name. Very weird. Okay. Nothing interesting going on. Mem copy. Oh, D. Oh wait, this is the key. The key of JSON. Oh, that's good. So it checks if it's D and if it's correct. Oh, fuck yeah. And now you see we're debugging this endless mess of this MBA obfuscation. So we are basically screwed. We need to skip all this and just jump back down to here. And this is still not enough. I assume we really need to do something about it. And this is where my idea started. Another idea that I thought about rose up. I needed a way to know where exactly I have to look at these obfuscated functions. So this function is about 1000 lines, let's say, of assembly. I really needed a way to automate this and put a breakpoint or a comment to the lines that have a call to another function. So most of this code is useless. The only code that I cared about is if I show any call instruction that calls another method. So with this way, I knew that I cannot really explain that right now. Give me a moment. I will confuse you more, and it's not that hard as I described it. So, okay, for example, you can see that all of this code is super duper garbage. Okay, but down here you can see some method calls. These method calls are certainly not garbage. You can see they're not obfuscated, they're just plain calls. So we need these calls. You can see that this is some register operations that seriously we ended up here, and after all of these operations EAX is just 0. So you can see that this is basically obfuscation of setting EAX to 0. This is insane. So main garbage. So basically we ignored everything, but back then when I was trying to solve the challenge, I needed a way to know what functions are called at each function. So for example, let's take this function. Oh, this is the main. I have labeled this as main. Okay, all of this time we were just at the main function. Okay, this is out of main function. All right, so check this out. Let's find this function here. Oh no, 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 no. Okay, let's find this function here. Okay, so this is the main function. Let's sort by length. So this is 8 to 1. This is this function. You can see that this function is enormous. It's even larger than main. But when I was trying to solve the challenge, I needed a way to know, okay, I cannot decompile this, but I want to know which calls this function actually does. I want to list all the calls that this function does. So I created an automation script that parses all the method assembly lines, inside x64dbg, right? I will show you in a while. Give me a moment. And it just dumps into a file all the methods being called inside this function. So what I could do, I could just breakpoint to each function of them independently and figure out what they do. For example, let's go to, yeah, this is it. What's this method? I see. So right now we are at the main function, and the one that was labeled as main function. You can see that I have left a string here, not my fault. It says extract JSON value. Okay, in case there was not this comment, you could actually debug this and see that, okay, you see D. So this method receives an empty a malloc, a memory allocated area. It receives something else, I don't know, R8, R9, I don't know. But when this method is called, you can see that the contents of the value of the dictionary of this JSON is returned. So I saw that when I run this method, the value of the key D was returned. So I assumed that this is extract JSON string value. And you can see that this is hex, and with str to L it's converted to a number. This is base, wait, str to L. Where is the implementation though? Is it here? Oh yeah, you can see that. Can you see that? So 085D8EA2, 085D8EA2, 82DA, etc., etc., until D560. D560, where is it? D560, here you are. So this entire thing is basically this hex string converted to row bytes. So 085D, all of them are converted to row bytes. Okay, this is very convenient. So, but first, So we figured out what basically this main function does. This large main function with these many bytes basically does this thing. It extracts this JSON value and converts from hex to bytes. This is all it does. But again, with the MBA obfuscation, it is gigantic. So let's figure out a way to actually figure out let's find a way to figure out what methods are called inside all of these big ass functions. So let's take the script that actually made me help me do this. It's called dump MBA calls, and it's basically as you can see, it's basically an IDAPython script, right? It's not an x64dbg script, I was wrong. It's just an IDAPython script. So what does this function do? What does the script do? It iterates over all of the functions. It gets the function length, forget about how, and it checks if the function starts with sub or MBA. If the length is greater than this number, I will show you how I ended up with this number. You see that this is 1EB3. If we go, okay, we don't need this anymore. Let's close this. Okay, so 1EB3. I really don't know why. Yeah, this is how I figured out this length. I saw that any function with length less than that is not obfuscated at all. With 1EB3, with the length of 1EB3, all the obfuscated functions begin. But apparently, these functions that have 40, 42, for example, yeah, I really don't know actually. Wait, let me check. I think I'm gonna change that. Why it takes so much time? Anyway, let's move on. So if the function length is greater than that, then we get the name of the prefix, and then we get the prefix basically, yeah, and we rename it. We basically rename the method. Okay, now if the function is greater than that and it starts with main, okay, oh, it's or. So yeah, this is or because we want also the main function to be included in this script, right? So we also want the main function and those that have a length such large. So in that case, did it finish? No. So what it does, it basically runs over all of the assembly instructions. You can see it runs over all the assembly instructions. Okay, this is basically decompiled, but it's enormous. So apparently, yeah, these methods are also obfuscated, so we need to include them in our script. Okay, what can I say? All right, so we iterate through all of we get the last assembly instruction, and we iterate over all of them. So we basically run over this, then that, then that. We iterate over all the instructions, and if it's a call instruction, we get the function being called, and we dump them, and we dump everything to a file. So for example, let's run the script, but run it for only one Do we actually need this? Don't need this. Since we call it just once, we don't care about this. Okay, so let's go here and Alt F7 and yeah, let's run the script. There is an error. No such file or directory. Yes, of course, we don't have the calls folder. So we created the calls folder and let's open this up, dump MBA calls, and it's done. And we get this file. So what's the method? It's 9600. We can see that 9600, which is that. This is, I think, obfuscated. Kinda. It's not obfuscated. So why the fuck did... I don't understand. This is not obfuscated at all. Why did I do it? Yeah. What? Let me change something because I think that this is too much. Alright, so for example, take this. Let me check. Oh, my brain hurts with the glasses. Oh, okay. So this is a mayhem here. This method is obfuscated as well. Of course. What about this? I think this is too. Okay. So why did it pick? Yeah. This is name. Uh-huh. Oh. And it did not rename it at all? What? Okay, it's deobfuscated. It's compiled. Yeah, it's obfuscated as well. So all of these should be handled by the script, but they're not. Let's rerun this. Okay, and it did not like that. Let's rerun this. Wait, which script am I running? Okay, cool. But I add the break here, right? So yeah, this is it, I think. Okay. We don't want this function at all. It's not obfuscated. What the fuck? What? What's the... Oh, this is a false positive then. Oh, okay. This happens to be larger than the target size, but it's not obfuscated. So let's run it. Let's let it run actually. Let's let it run. And dump everything. Okay, let's run this. You can see all the txt files being created here, and the Python script runs. You can see, for example, this is the main function. You remember 1590? This is the main function. What? No, what's that? Okay, 15 main. So you can see all the call functions being called. So, for example, 61.6c. Okay, this is not apparently it. It's 1590. Yeah, we're right. Oh, okay. So this is so this is 616c. Yeah, apparently. Yeah, this is it. So you can see that. You can see that, for example, 6189. 6189. So we know this is str to L. Sorry. So you get the idea, right? To L. Stop it. Okay. So this script basically dumps. This is how I solved it. I know there are more efficient ways, but this is how I did it. And this script basically dumped all the calls. So for example, this one is str to L. 616c. This one is extract JSON. No, sorry. I will replace all occurrences. Extract JSON value. Find next. Yeah, there are two of them, so we replace both. So we know here that this function is called twice, for example. If we scroll down, yeah, it's not. You can see that, look at the offsets. Here it's 619e, and then it's 952a. So there are about 3000 in hex lines of garbage. Then is C9e, there are again 3000 lines of garbage. After this, again 3000 lines of garbage. Here again after 3000. There is too much garbage going on. So, oh yeah, okay, the script finished. And we have 114 txts being dumped. So we really don't need IDA anymore, and we can focus only on these txts. At least this is how I solved it. After quite a lot of troubleshooting and debugging, my calls folder looked like that. This was a lot of work. I'm not sure I will showcase everything right now, but anyway, you get the idea. For some reason things are not renamed here, but imagine that everything below from here, anything below this point until anything until here is actually MBA-obfuscated. These are a lot of functions. Okay. What about this? This is not obfuscated, right? Yeah, this is not obfuscated. And actually you can see this is a JSON validation function. And you know how I understood this? Look at this strings array. And I remember this actually. In fact, there were some error strings that I looked up and I found out that this is indeed an open source library doing JSON validation things. Oh, this is maybe HTTP related as well. I don't remember. Oh my, never mind. This might be HTTP related. Anyway, we don't care. Good thing is that we have a full trace right now. So assume that, okay, all of the functions, all of the function calls are done, and now the obfuscation happens again. But we don't care, because we can just get into this offset. But now we have another problem. The addresses are not the same in x64 DBG and IDA. This is another problem. We have to rebase the IDA database. We have to rebase it to have the same addresses as the x64 DBG. So how do we rebase? You can see that the text segment here starts with 7FF744E4130, but here, how it's like that, yeah. But here the base address is completely different. In fact, we have to change this to take this. In fact, no, we have to take the base address, the base image of the binary, go to edit and do go to rebase program, segments, rebase program, and replace with our base image. You can see that this is the image base. If we select address of the first segment, it asks for the text segment, so it's we pick this number. But since we selected image base, we just select the first, this 4 zeros. So yeah, 4 zeros, and it fixes up the whole program immediately, and it also rebases the whole image. It also fixes up the relocations and everything. It's done automatically. So if we do it, boom, it worked. Problem is that the functions are still not renamed, but this is not a big problem actually. Oh, it's still rebasing actually. Wait, I think it will be renamed. Let me see. Oh, it's outdated, yeah. You see, it says outdated. That's a good thing. Nice. Fuck, I don't like this italic thing. I will change it anyway. Okay, while it fixes up. Oh yeah, everything is renamed. Perfect. You see that? Awesome. So 1590. So now you can see that again we are at the obfuscation area, the obfuscated area. So let's remove all of these calls and run the script again. Why? Because we need the new addresses. So let's run it, and again it will work as expected. So what's this method? This is C1 1590. Cool. Do we have this method? We have it. No, I don't want this. So C1 1590. Yeah, this is, for example, extract JSON value, and this is str2 long. Okay. So assume that we want to go to the next function that actually makes sense. We just pick this address, and we go here, press Ctrl G and jump to it and put a breakpoint. Okay. I have a name here, label already. I will remove it. Pretend that you never saw that. So I will put a breakpoint, and interestingly enough, we see some stuff being passed. For example, we see the value of RCX being this thing, this 32-byte value. This is quite sus. Second argument is oh, this is the ciphertext received from the JSON. You remember that? 085D8E, 055D8E, and it ends with D560. So this is the ciphertext, presumably. And R8 is this weird string, rusty at desktop. Okay, this is my PC name actually. If I write who am I, this is basically my PC name. This is my username and my PC name. It's not confidential, I don't really care. So let's get into this method. This method, again, it's obfuscated. But, so let's check its name. It's A6BA0. So let's find this name here. A6, so it's A6BA0. It's not. What happens? Why? What the heck? A6BA0? Yeah, here you are. This is, look at this length. Look at this size. A6BA0. So what the fuck happened? A6BA0. It does need .txt, no? So, okay, 744 EA. Here you are. Why it did not came up in the search? I don't know. Anyway, this is the method. All right. So let's immediately jump to this method. You see here. Basically, you know what? Assuming that, this is the ciphertext, then we can do two things. We can either breakpoint at the next function call and see what it does, or we can put a hardware breakpoint onto the ciphertext and check when it is accessed. When the time it is accessed, it means that the decryption routine has started. This is a good idea. Basically, I will go with this idea. So let's find the ciphertext. If I remember correctly, the ciphertext was in RDX. Yeah, this was RDX. So let's remove the existing breakpoints and let's put a breakpoint, a hardware breakpoint onto this. So let's run it and boom. Oh no, this is a breakpoint to the function. Okay. Let's run this. It's quite small. RCX is pretty useless. This method really does nothing. Anyway, let's run this. Okay, and it hits the breakpoint. So look at this. Rax plus RBX, and the result is stored in ECX. So this is basically the first byte. So if I understand correctly, RBX is the counter and RAX is the encrypted string. So RBX will iterate through all of the bytes of RAX at RAX. Okay, so ECX is accessed. Then look at this. RAX has now this value, which looks like, okay, this is another story. This is basically the ISS box. One experienced eye, look at this. What the fuck? Is flare on? 2019? Okay, check this out. AES box. AES box. So you can see that this is basically the AES box. You can see that 7B, F26B, F26B. So these 16 lines, yeah, until here, these 16 lines are all bytes of the ES box, right? Okay, here is the AES box, and apparently it's used. So it looks like the first byte of the ciphertext is used as an index in the AES box, and the result is stored at R10. Then there is something else being stored in RAX, and this is okay. This is a value stored here. Okay. No, sorry, I won't follow in dump this. Okay, this is a value, okay, stored in AX, and it's increased. Okay, apparently this is trash. Yeah. Okay, let's see where R10 is accessed. Right? Yep. So, as you can see, this is a decryption routine that is itself obfuscated again with MBA. Like, MBA is everywhere. Everything is obfuscated with MBA. Okay, this could take some time right now, but we can again. How can we deal with this? Okay, listen. We can take this address. Right now I pressed Alt Insert. Okay, I took the address and I jumped into IDA and go to this address. So right now let's highlight R10 and find all the occurrences of R10. So where is R10 accessed? Again, let's scroll down a bit. Okay, where is it accessed? It's not accessed. It's not accessed. Nice. The heck? I didn't actually remember this. Such weird. Okay. Nice. Oh, this is painful right now. Okay, suppose let's go to the next method call. So let's jump to this method here. So let's jump here. Oh, syntax error. What the hell? Hardware breakdown. Something is fucked up. Okay, let's run this again. Okay, shutdown. Oh, this is the encrypt decrypt method. Yeah. Okay, so let's rename it to decrypt good request, let's say. So what's the address of that? A6BA0. So let's rename this to decrypt good request. Okay, and I think it's called once. Yeah, okay. We could go ahead and decompile this, but it will take quite a lot of time. I'm not sure I want to do this right now. Okay, so let's run this again quite a bit, and actually, wait, what? Did I? Wait, what? What happened? No. What? Let's run this again. Okay, we do not want a breakpoint to shut down again. Okay, decrypt good request. Let's go inside and let's put a breakpoint actually to, let's go to RDX, and we want to set a breakpoint not only to the first value, to the second value. So to the second value, and also we want to set a breakpoint to this 32-byte thing that looks like a key. It really looks like a key. So let's set a breakpoint there, and also to R8. R8, oh, this is the date. This is the date today, 24th of January 2016. Okay. So yeah, let's go here. Oh yeah, this is my name, and let's put also a breakpoint here, and let's run this. Okay, next. Okay, it compares. This function really looks useless. Really useless. What's this? This function also looks useless, so let's skip it. Yeah, of course it's inside memmove. All right, so apparently the string is copied here. Let's put another breakpoint. Oh, there is also already a breakpoint here. Yeah, there should be it. We need a breakpoint here. Oh, there's already a breakpoint here. Anyway, okay, let's scroll down a bit, but I don't think that. Okay, let's. An exception? Seriously? Oh. RBX, RAX. What's the size of this? It's 100. Oh, look at this. 0x97. This is the size. So RAX is the maximum size of the ciphertext. This is the size of the ciphertext. 0x97, which corresponds to 151. And the current offset is at 1. So this is basically the point. This is basically the decryption routine. Look at this. It compares the RBX, it increases the RBX and moves to the next byte. So this is where the decryption routine ends. Look at this, and this is R10. Yeah, perfect. This is basically it. What's that? Yeah, okay. R10. What's that? Okay. RBX, and it subtracts something. What's that? Oh, it's a counter. Okay. So it starts again and moves to the next, etc., etc. 5D. potentially this is the decrypted ciphertext byte. How was this 0x5d XOR 0x8 55 CHR U? I don't know what the fuck is this. What is okay, I see that everything is stored in the stack, so this, what does this contain? Oh, this is there it is. So let's put a hardware breakpoint to this byte and let it run. Here you are. So it was accessed again. And let's see. Set a hardware breakpoint here at write access. This is where the decrypted ciphertext will be stored. So we need to set a breakpoint, a hardware breakpoint of write access, and see when it will be written. But first, this is the S-box thingies. Okay. Okay. This is R10. Why the fuck is R10 being used? Nowhere. Literally. Ah, too much assembly. Am I blind? Where is R10 being used? Nowhere? Oh my god, my eyes. I cannot find it. I really cannot. Oh. It's weird. Oh, here you are. Oh, this is the S-box thing. Oh, yeah. This is it. Look at this. Here you are. So, okay. This is part of the decryption routine. You see that? So, look at this. This is the offset. I don't know. Actually, it's part of the decryption routine. So let's take a look. It stores the number 2 in AEX, then it divides by RDI 15. We still don't know what these values are, but we will find a way to figure out the decryption routine. So it stores this number. Oh, this is the string. Okay. It stores racks. Oh, I see. I see exactly what's happening. Okay. So. Okay, I see. So, it takes a random character from the string of my username at my PC. It takes the character at index RDX and XORs it with the value at R10, which is 65. We still don't know how R10 is, what's the value of R10, but we have progress. Okay, we have progress. Now we can go up and find for any R10 occurrence. Here you are. Exactly. So let's put another breakpoint here. Right? Is there another reference to R10? There is a pattern, as you see. There are some conditional things, then just a bunch of obfuscation, then again there is legitimate code here. This is the beginning. We have already set a breakpoint here. This is the ISS box that we talked earlier. So we have breakpointed to all the important sections of the decryption routine. As you can see, the decryption routine is split it into parts, and between there is tons of MBA-obfuscated code. So let's rerun from the start. Now that we have all the breakpoints. So this is the good request. Okay. So, oh fuck, we missed it. Shit. What's the address? Oh my. Okay, let's put a breakpoint here and remove those and run again. We want to be complete. Okay, so RSI is accessed. RSI stores the ciphertext. Okay, so we take the address of the ciphertext and it is accessed at index RBX. So the first byte is stored here. Yeah, this is the S box. This is the offset to the S box. And here the obfuscation happens, so we press F9. So we subtract AL with BL. Where is ABX? Here you are. And it adds R10, which is the value from the S box, with FF. So what basically happened, it's this value. You see that? So this is basically 0, 1, 2F, but it moved the value to R10B, which is basically the last byte of the R10 register, so it's just 2F. Make sense? So only 2F is stored. Okay. Now again obfuscation. We skip through it. Then RBX is stored into RAX and div RDI. I don't remember exactly what div RDI does. Performs and assign the 64-bit decision combined RDX the RX. Okay, so okay, it looks like it divides RDA. I don't know, something like RAX divided by RDI and stores the result in RDX. Oh, it stores the, yeah, it remainder. Okay, okay, so it divides RDX by RDI and stores the quotient into the RAX and the remainder into RDX. Okay, so everything is 0, so the division, the quotient, and the quotient is 0. Anyway, we don't care about the details so much. So it stores this value into RAX. This is our username and PC name, and the result of the division, the remainder, is used as an offset into our string. Oh, so 0.15. It makes sense. Look at this. Look at this. 21. This is exactly the length of my username and PC name. Look at this. This is 16, 17, 18, 19, 20, 21. So basically, yeah, the remainder is an offset in index to our PC string. So it's like that. RDX mod length was something like that, right? This is basically what happens, and the result is XORed with R10B. with art&b being you remember this sbox thing, ct is our ciphertext. Let's write the entire thing, something like that. And also there was this, something like that. Yeah. Something like that. This is, yeah. Okay. And again, garbage code. R10 is the resulting ciphertext byte, the resulting plaintext byte, which is stored into EDX. Garbage things happening, and the decryption routine restarts again from the beginning. So we are able to implement this in Python. Of course, there is no other programming language anywhere. So let's take this sub-cipher thing and copy it to our folder, sub-cipher. So if one spends some time and debugging, troubleshooting with errors and stuff, they will eventually end up with this simple decryption routine. So it's a common name. I have named it common name. I don't know why. This is my name. This is my old name actually from the old PC. I have formatted now. it now. This is the ISS box that I talked earlier. I converted to a list of bytes. And yeah, the decryption basically is just like that. Something like that. You see, this is common name. So common name. Oh, RDX is the offset. I was close enough. Yeah, it's basically this is end, and yeah, you subtract e+1. Anyway, this is the decryption routine, and with some troubleshooting one can find out that this is the encryption routine. So I have a test case here, so you can see that I can basically run the script, and you can see that the assertion works, which means that decryption is the inverse of encryption. So this successfully inverts this. But now, what's the point of all of this? Like, remember that this is what was present in the... Oh, I need some water. Oh. This is what was sent in the traffic, what was captured in the network packets. So this is a ciphertext. So we know the ciphertext. We know the ciphertext. We know the sbox, but we don't know the plaintext and the com name. Or do we? This is quite tricky here. Yeah, I just got a flashback. That's why I crashed. Okay, it's a bit weird. Yeah, I remember now. We still have a long way to go. Okay, no problem. So this is basically the decryption and encryption routine of the how can I... Oh, I need a break. This is basically the encryption and decryption routine of the GOOD request. Okay, so we have successfully replicated that, and eventually, after all of this, Where is actually the result being stored though? We cannot find this. Where is the result stored? Anyway, let's get out of this function. Okay, we don't need the breakpoints at all anymore. Let's remove the breakpoints. Okay. Oh shit, I pressed F9. What's that? Okay, I think we were like, you see a lot of operations happening here, of course. Where are we? What is this method? I'm lost. What's this method? Oh, this is decrypt skill. Okay, we need to get out of this function actually. Let's get the fuck out. Actually, let's see where R10 is accessed after all of this. This is getting annoying. Oh my god. Oh my god, it's still running. Where the heck is R10 written? Oh my. Decrypt R10. Is it at the beginning? No. Okay, we need R10 though. Get out. Where is R10? Is this it? No. Ah. Did it run? No. Oh my god. Fuck this shit. Let's jump to the end of this function. Let's run this again. I think we don't need receive anymore for now, at least. Okay. The function ended. Alright, so let's see. Alright. So we can see that this is the plaintext after decryption. This does not look like it makes any sense, I think. So that's a problem, I think. So let's move to the next function. So the next function being called is this one. Let's get here and check the first argument. This is 36, apparently. Look at this, interesting. Assume that you didn't see that at all. Okay. I don't know actually what is 36. What the fuck was this? 54? I don't know what this is. Seriously. I don't know what is 36. I don't remember. Anyway, let's run this. Look at this. Okay. Okay, so this function receives RCX, RDX, where RDX is... Oh, RDX is our plaintext. Okay. What about R8? R8 is 36. Again. Okay. Anyway. It crashed. Why? I will show you right now. Let's again jump to this method. Okay, I think we don't need to breakpoint anymore at this. And let's breakpoint here. We don't care. Okay, so not to this, sorry. Was that what was that? This is, I think it crashed here, right? Okay, so it crashed here. Why? Okay, this function is not obfuscated. Let's analyze it in IDA. 7190. 7190. Okay, let's see what it does. Yeah, it's small, but my PC is lagging as hell, and the video is already 3 hours in. Whew. It's not easy. God, why it takes so much time? It's such a small function. Fucking asshole. This is it? Okay, this is it. So, what's going on here? Enable, okay. Yeah. We really don't know what's happening. Let's breakpoint. Okay, it works fine till now. This worked also. Oh, look at this. JSON exception parse error at line 1. Syntax error while parsing value unexpected square bracket. You see that? Square bracket. Expected unexpected that, expected, or either opening square bracket or opening curly braces. So if we look at this error, I think, oh no, if we look at this error online, yeah, exactly, I remember this library. Yeah, there is this library called JSON by N. Lowman, and this is exactly the JSON library being used in this program. So apparently this is the validate JSON method, and this is how I concluded that while I was solving the challenge. You see, when you see all the process, it's not trivial. Nothing is trivial, but when someone shows you the correct solution instantly, you miss all this experience of having actually to search online to find the library and understand that it's a JSON validator function. Everything is part of learning. Everything. We cannot just omit some steps in education. We need all the steps to have a complete idea of what we are doing. We don't want LLMs to rule us. So what we ended up with is that the result the plain text, actually the decrypt ciphertext, so this decrypted value needs to be a valid JSON file, right? Right. So for example, assume that, okay, you know what, we actually don't know what we have to what do we have to end up with. We don't know, we do not know. So let's try encrypting our own things. So for example, yeah, let's try, for example, to encrypt yeah, let's take a random dictionary, a random JSON, literally this, and encrypt it, encrypt this. Yeah, actually let's fuck this. Okay, makes sense, makes sense. We do not need to encode this as it's already encoded. Okay, JSON dump s. Yeah, we need to encode though the JSON inside. Okay, so let's send this and check out the result. We know the plaintext of this, so we know what we expect. Also, let's replace this actually with J, G, E, J, C, I. Okay, because that is our current PC name and we want decryption and encryption to work as expected. So let's rerun this. We have restarted the server and let's check out the plaintext. Where is it? What? Is it on RAX? No. Where is it? What? Wait. Okay, let's rerun this. Okay. Oh yeah. Nice. Here you are. This did not decrypt correctly. Why? The heck happened? Is my PC name wrong? Let's check what is our PC name. Rusty at desktop. Yeah, what's that? Yeah, J6GE J6GEJCI desktop. Alright, this looks correct. Okay, weird. This does not look like a valid JSON actually. You can see that. Where is the what? Yeah, decryption was not correct. What the fuck happened? Oh my god. And I thought it cannot get any worse. Anyway, you can see that validate validate JSON failed, of course. Oh my god. Yeah. Okay. Decrypt, encrypt, for JSON, JSON.dump s. Let's take the entire thing over here and yeah, let's print this out. This worked like a charm. What the heck happened? Oh my god. I don't understand. Let me run this and check my old solution. I don't know what's wrong. It just does not decrypt correctly. So where is it? Subcipher? No. It's server.py. Yeah. No. Yeah, I'm not doing something wrong. Oh, I'm doing? Does it need single quotes? I don't think so. Okay. No, I'm not sure. Okay, let's rerun this. Okay, let's go. Okay. Why? Okay, ra nd. Okay, the plaintiffs will be formed here. Oh, sorry. The problem was the double quotes. Okay, I should use single quotes. Anyway, okay, so validate JSON passes successfully. Nice. And let's go ahead. Some more probably JSON related functions are called. Oh, and here an ACK string is formed. So apparently this method decrypts the ACK string. Okay. So this basically apparently it looks for the ACK string inside the JSON object. So of course we don't have an ACK string, so let's create this it expects an ACK. So let's rerun this and go. ACK. Get JSON key. Fetch JSON key. It returned 1, you can see that, while before it returned 0. Nice. And it moves on to the next calls. The next calls are what is this function? This is what? EF. Oh, it's EF CF. Okay, this is it, so we don't give a fuck about this. This is string clear, so the next function is that. Let's go down here. This is where I'm seeing all this information, my txt file. Now you can understand why this is useful, because now I can focus only on the method calls and ignore the rest garbage things. So let's go down here and continue our debugging. Okay, the ACK string is accessed, and we can see that it extracts a JSON string object. The value, of course, is JSON. You remember that it was ACK JSON, right? Alright, we're already 3 hours in. So let's move to the next method, which is this is 36. This is it. Okay. Okay, there is a NAT symbol. EC30. Oh shit, this is not good. Oh, it expects, if it's an FFFF, it's not good. So it expects a NAT symbol, if I understand correctly. So something at else, for example. Let's rerun this. You see, this is trial and error. Like we try to understand what's going on through the errors that we get. So let's go ahead and validate again. Fetch JSON key. It's good to go. Let's run this. It extracts the JSON value, something at else, right? So it extracts the JSON value, and fuck yeah. So this is probably the substring. No, let me show you. Yeah, the length is 9. So this function checks if a specific character is present on the string, and if is present, it returns its offset. It returns, yes, its index, its offset inside this string. So the offset right now is 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Nice. So let's move on. Okay, again, next non-garbage method is at this offset, which is string copy. It copies something at else. Okay, so what does this do? It checks something with Rusty. So okay, so this is our username. Okay. I don't really understand now, but let's move on. Okay, let's move to the next. It checks Rust with else. I don't get this. Let's move to the next. What the fuck is this? This returns 1. Okay, this is not good. Oh, what's that? Okay. Oh. And apparently it will exit now. Yeah. Okay, I don't really... if I understand correctly, it should be something like that. Like it checks whether the first or the second part of the string is rusty. So if we can generalize it, it checks your username. Like it checks your username if it's in there. Okay, let's put it in the first. That's the first element and rerun this. You see that it expects a lot. Oh, we need to restart the server. Yeah. Okay. Okay, let's continue. Okay, this is the offset. You will get character in string, something like that. Okay, let's move on. String copy. Oh, huh. Okay. 060 61. Oh, this is tough. 6D1F. Wait, are the... Oh my god. Are the offset changed? Is the base offset changed? Oh my god. I will have to rerun the script. Please no. Please no. No, thank god no. Okay. Okay, then what? 6D. Okay, let's run this. Oh, okay. This is another string copy. 09F99. 09F9, here you are. Okay, so this is string copy. Okay. Okay, it's else. What does this method do? I don't get this. 749D0. 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 Where is it? 7. No, what's the method? 744E749D0. Here you are. Okay. So this method basically calls just one function, which is essentially this at the end and nothing else. And what does it do? It's just a mem move. Not what? I don't get this. Oh, 9 fd4. Oh my god. What? I really don't know what's happening now. Why though? Why is that happening? What does it do? This is a good function, we can just decompile it. Okay, let's wait. I don't get this, seriously. Does it expect another key probably? Second. I honestly, I'm not baiting right now, but I honestly don't remember. So I'm troubleshooting just now. Okay, let's run this, get character. Okay. Okay. Whoa, 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 whoa. Spoil. Jesus. Okay, let's run everything. Are we expecting? Let me check. I'm gonna cheat again. What the fuck is this? I even forgot what this is about. Anyway, okay, let's go ahead and run this. Yeah, it just exits and stuff and stuff. Yeah. 3b 3b6e. Maybe it just moves on. Don't know. Okay, let's skip this function as well. Oh, it does. Super cool. Okay. Not NA. Oh, this is a conditional. This is the function of interest. No, this is not. It's memcopy. Oh, so it keeps track of this. So is this NA? Does it help if we actually run API monitor again and see what the heck it does with that? Will it help? So it's BEFC, BEFC, BEFC. Here you are. Next one. Oops, spoil. Yep. What the heck? What the heck is it talking about? What the heck is it talking about? Okay. So let's set the breakpoint here. Yeah. Okay, so it calls this method. Forget about this comment. Pretend that you do not see that. Okay, so it takes the thing after at, so this, and fuck. So let's see what happens after this method. Oh, it crashed. Shit. Okay. So what does this do? Let's take this method and throw it into IDA. Let's see what it does. Oh. Huh. Good. HTTP scheme is not supported. Story argument range. Oh. So what is this exactly? This looks like a domain, a URL. So it's HTTP / it escapes the slash. So it's colon. Okay, it looks like it expects a URL, a domain actually, a domain in the here. So for example, something like that. Let's run again. Okay, validate JSON, we don't need this anymore. Okay, this function is good to go now. Okay, what's that? It crashed. So we need this breakpoint. Fuck. Okay, let's get into it. What is this method doing? Fuck, what the fuck is this? Okay. Is there some shit? And eventually this is a memcopy method. So nothing much to it. Yeah. So this is it. Forget it. So what's that? It runs properly. NA again. Okay. What does this do? Nothing. Oh my god, this man. BEFC. Okay, let's move the Okay, so my guess is that this attempts to read the domain here. Let's run this. It returned something, but I don't know what. It looks like it's running properly. Oh, what? The fuck? What? Oh my god, I must start renaming something because I'm lost. Okay. Check here. Nice. Okay, forget it. Let's pass through it. Okay. It looks like it's not crashing at least. Let's run this. Okay, let's skip it. What the fuck is this? 5,000. Okay. So what's this method? 13E60. So it's 7444F1 3E60. Oh, here you are. We have this, and it looks like it does some stuff. Okay, let's start with this. Okay, RCX. What is the RCX? Nothing. BEFB0. What's that? Something about time? The heck? This is memcopy. It's 23. What is 23? Oh, the time? It's 2 hours behind. Don't know. Anyway, let's move. Oh crap. Spoil. Ugh. Okay. We know it's IS, so I will leave this message. Shift times then F9. Okay, mem set. Okay, it takes my username, it does something, I don't know what, I assume that I don't know what, and it moves on. How is the program still running, by the way? I'm starting to lose it. Oh, what? What? It returned some info about my PC? This is some system info. Okay, interesting. So it returns system info. Let's use API monitor, please. Please. For fuck's sake. Let's enable anything related to, don't forget it, it's good as is. Okay, let's go to store and let's run this. Oh, fuck you. I pretend that I don't know that. So, okay, the part after the @ symbol is the domain that it's connected to. And since I did not provide any port, it expects it to be, the default one is 80, right? So it connected to this domain and it tried to send this data, my data. It sent those data, but they cannot do anything. Oh, you can see that this sysci, oh, so this is the command that it executed on my PC. So my PC is the infected machine that runs these commands. And this one is system info, sysci, system info. And this is the encrypted JSON that you show with my system information. So we have to provide the correct domain here. And of course, we know the correct domain because we have the pickup. Look at this. This is the exact domain that we should use. Look at this. This is the exact domain that we should use. Nice. But of course, again, this domain does not exist. Okay, it's a rickroll, but we want to edit our host's file and point it to localhost. All right. Yes, this is an admin page. Okay. Okay, so we need a step back now. Let's refresh it, start from beginning. So we need to set up another web server now. Okay, we need another web server. Of course, we will take this web server from my files here. I have this server 8080. And let me open this so I don't spoil you anything. Yeah, fuck this. There are a lot of spoils here. Huh. A lot of spoilers, Jesus. Okay. 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 Global IV. Okay. Looks good. So it's 1 AM already. Great. So this was very useful actually. Let's close this again and let's go ahead and run the other server as well. Module not found. Okay, I forgot pawn toolsy. You will see why. Okay, the server is running, so let's run this again. So check here. No, we don't want to check here. Let's debug this through a bit. Okay, you can see something. An experienced eye might notice that the IS key, this function says constructs the IS key, right? Even if I hadn't renamed it, one can just go here and notice that, hey, this looks like the IS key schedule. How do you understand? How did I understand this? You just iterate through this function. See this? Yeah, basically reverse this thing. Where is it? No, this looks familiar. What the heck? Okay. Yeah, this is the IS basically. AES. Anyway, one can deduce that the actual username, the username of the author that created the challenge, and their PC name are essential for the encryption of the traffic. So the encryption key and the decryption key of the commands that we saw on Wireshark are related to the username and the PC name of the user. So this is essential because our username is Rusty, and certainly the author did not use the username Rusty. They used their own such name, and we have to know what was this name. Okay. So our task is to figure out the username, and this can be achieved via, let me see the subcipher method. Where is it? Subcipher. Yeah, this can be achieved via yeah, let me remove this. Yeah, you can see that the username is actually used for the decryption and the encryption of the good request. So we will figure out this part from the decryption. We will see how in a while. For now, let's set up the server and run it. Okay, it's already running. So let's go ahead, and I see some methods that I don't even know what they're doing. Anyway, it did not connect to it. What the heck? Did I restart it? I did not. I think I did not. Oh, there is an error. What's the error? Oh, there's an N. Yeah, forget it. I forgot it from the solution. Read content length. Okay, interesting. Let's restart the server. Yeah, let's go. Payload is not defined. Yeah. Okay, we assume that again the body has to be valid JSON. Actually, it looks like everything has to be JSON. So yeah, this is encode. Okay, let's keep it clean. Let's rerun this. It should work now. Something happened. Oh, fuck yeah. So we managed to replicate the exact traffic. This is a post request from this host. The body is this. So this is basically my system information being post requested here. You can see that this aligns with this. This is the system information of the challenge though. You can see that. And the server responds with something. No. Okay. Okay. It didn't, and it crashed. Oh my god. Give me a moment. What is happening now? I'm not really sure. Okay. This is getting annoying. Okay, this is my name and it's used for the IS key, as we said. Okay, we will figure it out later. Okay, and it's what is 23? Ah, it's the time, right? Yeah. Okay, and I think that RAX has the, yeah, this is the IS key. This is the actual IS master key. Okay, now how it's used is another story. How it's created is another story. We will take a look at this in a while. So let's go this function, and please no, I hate you, motherfucker. Okay, let's go F13E60. What's that? F13E60. Yeah. Okay. A8E5. A8E5. Okay, let's go here. No, here, and breakpoint to the next. Now I'm really lost. I don't know. I really don't remember what I have to do. I'm really lost right now. I'm really lost. Nah. What's that? Okay, I somehow need to see how this data is encrypted, because here I do not see how this data is encrypted at all. I need to find this. So first of all, I need to find I need to breakpoint to send first of all, because we know send is called to send the data, right? So let's call this, let's rerun this. Okay, not first time. Is this data sent? It's not sent. What the fuck is this? It's better not to have breakpoints at all than having useless breakpoints. So it looks like this is the post request being made. Here it is. It's a post request, but where is the body? Oh, the body is another story. Oh, here you are. Here you are. Here it is. So yeah, the encryption has already happened beforehand. Yeah, so the encryption has happened already. Where is the encryption being done? Okay. Get username. I'm gonna try that, but I'm not sure it will work. Okay. An established connection was aborted by the software on your host machine. What? It broke up. This was fucked up. Anyway, it got the request though. Okay, we need to find out how this is being made, and of course to find out how the decryption key, how the IS works, we need to find out the actual username because it is part of the encryption key. Also the PC name. Apart from the username, the PC name is also useful. Okay. Let me check something up pretty quickly. Oh. Okay. Nah. Yeah. So at this point we have a problem. We have a big problem here. We do not look at this. You remember subcipher? Okay. So for subcipher, the PC name that we want, so this part, and the username are used and indexed like that. So the problem is that this is our local value. We need to see what was the PC name and the username of the author while they were creating the challenge. So we essentially need a way to figure out this part. So how can we do this? We actually know part of the plaintext, right? This is, look at this. This is the decryption is essentially just XOR. So it's A XOR B, where we need to solve for A. Like this part is unknown, we just know the @ symbol, but we don't know the right location. Anyway, this is essentially XOR, like A XOR B. We know part of the plaintext. We do not know the entire plaintext, but we know part of it. We know that the plaintext consists of this big string. So this big string, we are certain that this big string exists in the plaintext. Okay. Okay. And also, no, actually, all of that. AC and the ACK2. This entire JSON exists as is, right? So this sbox thing is standard. So we have part of the plaintext. We also have the corresponding ciphertext. So we are able to figure out the name, the PC name and the PC name and the username. And I have a little comment here. Yeah, it's the algorithm basically. Okay, so let's take a look at this. What happens? Can I import that? No. How can I showcase that right now? Okay, so take a look at this. How can I explain? Suppose we have A equals this big thing, right? And suppose we have like suppose we have our secret that we know is about, for example, suppose it's that long. Actually no, let's put it like that. How will the XOR operation work? It will start encrypting character by character, right? So T with A, H with B, E with C, but when the string ends, when the smaller string ends, it will start repeating itself to match the length of the original of the largest string. So the vulnerability in this crypto thing is that this part of the plaintext, which is known, this is known from Wireshark, this thing is part of the plaintext, and we are given this. So what we can do, we can actually go ahead and XOR this. So we can create a script. Actually, I have not created a script already for this. I wonder why. I do not have, really? I really don't. Anyway, okay. Let's take a look what happens with this. I think I'm gonna split this video in two parts. I'm too tired right now to move on. My god. Find PC name support, let's say, and it's like that. So known PT, right? Okay. So what do we know? This is our known plaintext. We are certain that this part exists, and we assume that the length of the username and the PC name are quite small, something like that. Like mine was this, which is relatively small. So we're certain that the PC name and the username will repeat like that. Make sense? Okay. So what we can do is okay. So we need this part, this S box. Okay, and the ciphertext, where the ciphertext is this. We want the real ciphertext. Okay. And what we can do is that how can I do this now? We know the plaintext, we know that thing, we want this. Okay. So we want to iterate through each ciphertext byte, and basically import XOR, let's do it like that, print XOR known plaintext with CT from I until the end, from I basically until the length of PT. Okay, yeah, this is essentially XOR. No, we don't know. Sorry. No. No. We want this part. So we want the S box as well. Okay. So I want all of this thing. current city equals from there for be in current city. Yeah, this is exactly it. Yeah, I think this is it. Maybe not. Name, PC name. It's known PT J comma J mod length known PT. It's a bit messy, I know, but I think it will work. So this thing shored with that thing and print the PC name. It should work, I think. Let's see. Find PC name. Yeah. With pawn tools. Find PC name. Let's go. Oh yeah. This does not look that it makes sense. This does not make very sense, right? Okay, let's actually try, and of course it will be printable, so let's try go and decoding it. If it doesn't, just skip it. Yeah, fuck. This does not work as expected. Oh no, this is J. This did not work. Let me check something up. So the current city is this thing, right? The heck? Is this correct? Yeah. So the PC name is XOR of PT known of known PT comma current CT. Yeah, this makes more sense. Yeah. Oh. What's that? Something is off. Okay. Wait. Okay. How can we? Oh my god. Okay, we can assume that at is known as well. But what part is? So my idea is that okay, city I minus I plus 1. Okay. I don't see anything that makes sense, right? Shit. Now we have to deal with this. Why did I not keep the fucking notes for this part? Why? Why? Why did I not? Whoops. Oh, I have this part. Hoo-hoo. Give me a moment. Oh yeah. Oh yeah, baby. I have this. I have this part. Here you are. So, what's the idea? What's in good? Yeah, in good basically is this. Okay. It's the encrypted response of the good request. Okay. So, what's the idea? We know that the plain text is something like that. For example, something at this large thing. No. Yeah, at this large thing. And we don't care about the rest. Now, there are a few cases here. Is it like that, or is there a white space here and here, or is it only here, or is only here a white space? We don't know. Also, we don't know the length of the name. So we basically here we brute force the difference between the encrypted and the known. So we take their difference, which is this is yeah, this is 151 bytes, and the non-plain text is 124. So there are 37 remaining bytes, and this is the room for the name, the username, and the rest of the JSON things, the curly brackets and stuff. So we brute force basically the length of this, and we get only we try to get only the ciphertext corresponding to this length. For example, this is the ciphertext. Assume this is the ciphertext. Okay, assume it ends here. So in that case, for example, we keep only this ciphertext. So then we brute force one more, and yeah, suppose we take this ciphertext. Then and you get the idea. then we remove one, we get this ciphertext and stuff. So every time we take the ciphertext part that corresponds to this non-plain text, and we try to find the key. This is basically the PC name. Okay. This is the encrypted sequence. This is j plus I plus 1. This is tricky to understand, because normally it's I plus 1, but we need to add the jth index as well. So this is how it works, and by running this, yes, we get the plain text, which is the boss at Thundernode. So we get the username, which is the boss, and the PC name, which is the Thundernode, and that's very good news, because now look at this. We can go here and from subcipher import decrypt, so we can go ahead and decrypt the encrypted with the PC name. No, actually, no, we cannot put it here. Yeah. No, you know what? We can put it here, actually. So, how can we? Anyway, let's do it like that, and for now. And good, this is good. The key is the PC name and the username, and this is this. My English are so bad. So this is the good key, and here you are, bam boom. This is the exact this is the plain text good request, that the good response that was received. So you can see that the username is not username, I don't know this, it's I don't know what this is, but anyway, it's not the username is the boss. So this must be something else, I suppose. So there is STA excellent and ACK blah blah blah. So this is, I think, okay. So let's use peanut here, and we don't care about the rest actually for now. But this is a plain text, alright? So after 4 hours and a half in the video, we got past the first part of the challenge. This was the first part of the challenge. Anyway, let's move on. This is insane. Oh my god. Let's do it like that actually. Code, right? So this should be just the JSON thing, and the encryption happens with the PC name, which is the PC name is the boss at Thundernode, right? Okay, looks good to me. No, actually we cannot do this. Yes, because it will decrypt with Rusty. Yes, we cannot do this. Anyway, let's copy this. Let's copy this as is. Replace this, the double quotes, because as you remember there is an issue with that. Okay, and this is the response. Awesome. So we got past this. Okay, cool. Let's go ahead and run this. Let's restart the servers and this. Okay. What? Oh, of course. It was fucked up. Okay, now we have to understand how the IS key is constructed. Let's go to the comments and go to the create IS key and place a breakpoint. And apparently this is peanut. Okay, peanut is used as well as the PC name and the username. So assume that whenever we look at Rusty at desktop, it's essentially the boss at Thundernode. So this is what the PC name and the username are supposed to look like. These are my own values, but of course they're wrong. We will never decrypt the communication with these values. We need the boss at Thundernode and peanut. So to construct the IS key, these specific things are happening. Let's analyze this function. So first of all, nothing interesting here. So let's go check this out. 65767 is 609 6A, and this looks like SA. SA. Okay, what SA? What with SA? There are a lot of SA. SA1, SA256, what SA? 67. Oh, this is SA256. That's perfect. That's really good. So E0, perfect. So this is the initial state of the SA256. Okay, good to know. Good to know. So apparently this is some SA256 stuff, and this is the SA256 internals, apparently. I suppose so. Okay, so this is some weird ass initialization. This is okay. So how is this called? Okay. And how does this work? Are they concatenated or what? So give me a moment. Where are we now? We are here. Okay, A8 C9. A8 C9. Oh shit. Stop. Okay, let's see the like that. A8 C9. Okay, here you are. What's this method? Oh, this is big. Okay. So what's the first argument? The first argument is probably the SHA-256 context. Okay. Peanut. What the fuck is peanut? Don't know. Okay, so this 32 bytes is just a hash. Makes sense. Okay. But what exactly is hashed? We don't know. Let's name it construct SHA-256 key. It's a hash, but it's actually used as a key. Okay, so yeah, construct SHA-256 key. As you can see, my current names are much more accurate than those names. Okay, so construct the SHA-256 key. What's R9? 00? It's the current time. Looks like the time. Okay, so suppose it's time. A3 is R8, which is user PC name, and A2 is peanut str. I don't know what the heck is this. Okay, and probably this is the SHA-256 context. Yeah, I assume it's the context. Okay, so what the fuck is this? Nothing. Okay, what's that? Oh, so this is, oh no, never mind. Construct, no, I was correct. Construct ASCII. Yeah, it's correct. How do you understand? Because look at this. The actual data are passed only to this method, and this method is called twice. So the rest is part of the general key schedule of this challenge. So this is where the peanut string is hashed, apparently, right? And this is where okay, so this is calculate SHA-256 hash. So what's this function? 79 okay. Oh, I have already named it. Calculate SHA. I like naming it with capital letters so they stand out, you understand? So calculate SHA-256 hash. Let me put a breakpoint here and see what we get. So first things first. So why? So RCX is our input string, R8 is probably the SHA-256 context. Don't know. RDX? What about RDX? What's RDX? It's empty. So let's call this method. Oh, okay. So let's see. Is it indeed the SHA-256 hash of PC name? J6GEJCI hex digest. Fuck yeah. F2435661E, F2435661E, 35, etc. So first part of the calculation of the ICE key is SHA-256 of the username at the PC name, the first part. So this is the first part, and then okay, this is the first part, then blah 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 blah, something else happens, then let's go to this line. This is where, oh okay, so peanut is concatenated with the current time that the script is running, that the program is running. So that would be peanut 00. So after having calculated that, no sorry, it's R8, yeah, boom, yeah, 0585 E4 C1. This is exactly that. So this part is SHA-256 hashed, so as this part, so as this, right? And what happens after that? We can see some XOR here. Okay, so what is XOR? I think I already know what's the answer, but let me make sure. Okay, let's go to the RSI. It says, oh, very nice. Okay, so RSI stores the peanut 00 hash, and RDI stores the PC and username hash. So basically it is XORed. Those two values are XORed together. You can see that they are passed to XMM registers, they are XORed and stored back to RCX. You see that this is their XOR. Then the rest are XORed and written also here. So you can understand this like that. Peanut 00 H2. So lambda XOR equals lambda equals lambda a comma b bytes he comma c for keeps. Is that correct? Yeah. So take a look at this. F7C6B2DF, F7C6B2DF. This is exactly the same. So this is how the key is computed, essentially. If we step out of this function, look at this. No. Yeah. Look at this. Boom. This is the 32-byte key being used. So now we need to solve this. We need the actual PC name and username that was used to create these keys, which is the boss at Thundernode. Right? Am I correct? Okay, let me actually create a script named solve.py and write down the PC name that it's like that. Okay, PC name equals that. Okay, and let me spoil a bit. Oh, Okay, where is it? Yeah, I am naming it identifier for some reason. Let's keep it as is, peanut. Where is it? So, okay, let's import XOR. No, actually, let's create our own XOR. Who cares? Okay. Okay, this is our XOR. Let's import SHA-256. So, #1 is the SHA-256 of the PC name, digest, and the #2 is the SHA-256 of the identifier plus H, where H is the time, and we need to find out the time just now, but the result is XORed, and this is the key. Let's print it in hex first, and then no, actually, just like that. This is cool. Okay, so find PC name. Let's keep it in a separate script. Okay, so of course this is wrong. We need the correct H. So how can we find the correct H? Don't forget that we are given the Wireshark, the packet capture. We just have to look at the date. Look at this. We just have to look at the date of the response and extract the time. And look at this, the time is just 06. So the time is just 06, and the encryption key is this, just like that. Okay, and we can verify that because in my notes I have also mentioned that. No, it's wrong. Wait, what? I think it is real com name. Yeah, I think it is real identifier plus H. Yeah, anyway, we will check in a while that this is true. Anyway, so we constructed our AES key. Okay, now we need to place a hardware breakpoint to which value? Here. Okay, so we need to put hardware breakpoint and F9. Great. So this is the function that actually uses this key. It is essentially where is it? Essentially, is that one? What's this method? Okay, interesting. This is called here, and this is called where? Oh fuck, this is not going to decompile never. This will take a century to decompile, so let's take a look at these values, I suppose. Oh, this is the ISS box. Nice. So this is the ISS box. Will decompile. Okay, what's that? Okay, this is the inverse S box. Again, you need to have seen these quite a few times to get familiar with, because now when I see these first 4 bytes, I recognize instantly that this is the IS inverse box. So 52.09685, 52.09685. So this, I think this is the IS Archon, as it said, is called IS Archon. I need to put my glasses because my eyes are tired right now, very tired. It's been 5 hours. I have not stood up at all for 5 hours. Everything for the channel. It deserves all the sacrifices. So again, being a little familiar with AES and recognizing crypto identifiers, this definitely looks like the IS Archon, as it's called. So it's 10, 20, 40, 80, 1B, etc. 10, 20, 40, 80, 81, 136. Yeah, this is clearly the Archon. Okay, so this is the Archon, IS Archon. And this is the IS inverse S-box. Okay. So one might confuse this that this is the IS encryption, but it turns out that this is not the IS encryption, but it is the IS key schedule, because we know that the Archon is used at the IS key schedule part. Look at this Archon, which is RCI. Archon I, this is used in the key schedule algorithm. So we know that this is the master key being passed to the IS key schedule, and this will return, of course, the master keys, which I don't know, but I think they're stored here. Where is... Oh yeah, here you are. This is the master key, and these are the other keys. Now, how many rounds is it? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. How many rounds in IS? 256. No, 256. 14. Yeah, so there are 15 round keys, excluding the first that is related to the master key. Okay, great. So now what we can do is put a breakpoint at any round key and let it run, and boom, this is insane. I love it, so satisfying. We immediately hit the IS decryption or IS encryption routine. If we take a look at this function, this is exactly where the IS encryption is happening, and this is awesome. So yeah, here you are, and it looks like it's ISCBC again. It might be a bit hard. It might be a bit hard to understand at first, but it makes sense if you haven't watched the reverse engineering Hackybird video, but it's in Greek, so I don't assume that you have. So this is, I explain what happens there, but I will try to explain here as well. So you can see that first of all there is some XOR first being done, and then the actual encrypt block of the IS is happening. And then this is a current block, right? Number of blocks. I think this is the input length. This is probably encryption, so plain text length, plain text size. I think this basically subtracts 1 and divides by 16. Yeah, so it splits it in blocks. Okay. So it actually XORs what's that? Oh, this is the round key. No, this is the let me check something. Okay, so okay, this is ICBC. Take a look at the ICBC. So take a look at this. In ICBC, the first part is a XOR of the current plaintext block and the initialization vector or the previous ciphertext block. And then the result of the XOR is actually encrypted. Right? So yeah, it's the decompilation is a bit weird here, but you can see that the actual thing being encrypted is stored in A1, and there is another XOR here. Okay. Apparently where is the result written? What? Anyway, I'm not too sure. Something's wrong with the compilation. I mean 5v7 is XORed with itself and then current block is passed, but current block, oh, it's the input. Okay, so it proceeds with it. Okay, so it proceeds by one block and then it encrypts it. Okay, so we have to figure out the IV. So we have the key, we have the plain text, but we don't have, we have actually the ciphertext, but we don't have the IV. We don't have it. We need to find the IV. So let's figure this out. We can place a breakpoint here just before the first XOR happens. This is where it happens, right? So let's rerun the entire thing. We don't need this. Okay. So interesting. Oh, perfect. You can see that this is the plaintext block, the plaintext, and this is the PKCS7 padding. So it's padded with 0 Bs, and this should be 96 bytes in total, as you remember. No, I'm fucking around. Wait, 32 for 64. No, it's much more. Anyway, okay. So okay, so RAX is the plaintext block, right? So CL must be part of the IV, and CL is part of R9. Okay, wait, this is weird. Okay, I'm not really sure. Let me run it a bit. Okay, CL is 1, then 2, then 3, then 4. Okay, and so it increases by 1. Okay, so the IV is basically this. So it's 0, 1, 2, 3, 4, 5 random until 16. It's that simple. Okay, so if we want to write this down like that, it's just this. So how do we know that we figured out the correct IS components? We can import the IS into pcapng and attempt to decrypt something from the packets, from the captured packets. So let's use the key IS mode CBC and the IV, and for example try to decrypt bytes from hex. Let's go here and for example grab this and try to decrypt this. If we run with pcrypted solver.py, perfect. Here you are. Amazing. So we are able to decrypt the traffic just like that. This is the system info and this is the padding. Let's make an assertion here that it's decrypted correctly, and this is our assertion, this is our sanity check that it works perfect as expected. Unpad this shit with comma 16 and boom, voila. If we changed something, actually yeah, for example let's remove 32 bytes. Oh, it still runs? What? Let's run the entire thing against. Yeah, okay, padding is incorrect. Anyway, okay, it works. So we are able to decrypt the traffic. So let's go ahead and grab the encrypted traffic. So for this I will use my existing script. So what happens here? Wait, what the fuck? Okay, I have already extracted the encrypted strings, so we don't spend any time with that. That's cool. So if we run this, okay, key, boom, magic. By the way, this is not magic. These are all the encrypted values from the Wireshark. So this is it. Then you can see that they are with the same order. Like this is 3B001A, then the response, request, response, request, response. It's one at a time with the same order as they appear in Wireshark. Of course, I could use something like some automated parser of packets, probably. There are, for example, tools that you can use with PyShark, for example, and tshark. Okay, PySark. No, tsark is, what is tsark? Yeah, it's not Python specific. Yeah, but PySark, it's a wrapper over tsark. Yeah, so one can use such tools and automate the extraction of the packets body, but I did it manually because I'm dumb. Anyway, let's move on with the rest. No. Okay. You can see that there's a lot of stuff here going on. Too many commands were called. You can see that there, it's actually interesting. You can see that there is a message and it says that it's a CMD. There is the D that contains the actual body, and it's the command ID and the actual command line. So yeah, I don't remember what this does, but you see that, for example, the malicious user asks the infected machine to execute this command, and you see that the response is literally the response of this command. So this command executed in the infected machine, and this is the response. So basically, this is the list of files under the documents directory. So LP, I'm not sure what this is, but okay, this is base 64. Let's take a look at this. What this is? Yeah, I get it. Some guys, they're happy just to turn the key and drive, but you gotta pop the hood. You gotta trace the wires. I feel the hidden camera of the block. You're not looking to steal the car. You're just trying to solve the engine. That's an honest, nice work right there. I'm not really sure what this means. Where am I? Here. Okay. I am. What's going on? I pretend that I don't know. Where the fuck am I? Oh, I found it. Okay. Okay. Oh yeah. All right. So and here is what where the problem starts. Take a look at this. Take a look at this. All this time, the server was sending malicious commands to not malicious. It was sending commands for the victim to execute, but there is a place at this point before this command, when the script attempts to decrypt this command with the key and the IV that we found, it apparently fails because the exact previous command consisted of a DT value being changed and NP. So we don't know what these are. We still do not know what these are. what is the NP and what is the DT keys. We haven't identified them. This is a command ID. We can see that it increments per command. Well, not exactly, but yeah, no, it increments by command. Yeah, correct. For some reason, what? This is the same as that? No, this is the boss. Yeah. Okay, so we need to remove this, and you need, this message is a hint. It tells us that we need to understand the soul of the engine, which means that it forces us to understand what does this NP do and what does this DT do. We're forced to understand what how they are implemented, right? Okay. So I still remember the time that when I realized, when I actually saw that I started copying all the encrypted texts from Wireshark, and once I pasted this and saw that it suddenly stopped working, I was like, oh my fucking! I had spent 12 hours in that day just to see that it fails after some specific message, and I was really disappointed. But eventually it was not that hard to solve. I will proceed. Give me a moment. Okay, boy, it's 3 AM. Jesus Christ. So let me copy paste the rest of the encrypted messages. We will use them in a while. Okay, so what does this NP do? Let me actually update solver 8080. Let me show you what I've done. So my original server 8080, basically I'm thinking something now. What if message no op, Jesus. I'm thinking I could basically send this alone. I could probably do that. Let me check. Okay, so this is the encrypted payload, right? Let's change the command ID to 2, and let's actually, okay, this is the, okay, this is what I did here as well. Okay, so is new key IV what's the key? Anyway, okay, pad payload, so until that, and send what? Send this. No, this is basically the body. We want to encrypt. Oh my god, I need to go to the bathroom. But first let's check what's going on. Enc body. So this is enc body and this is the payload. Be right back. Okay, back. So let's send this body, and yeah, we need the key and the IV. Where are they? Okay, and okay, the IV is just this, so nothing much to worry about. The key is, where's the key? The key is just this. Okay, the key is that. All right, so let's go ahead and attempt to run this. I'm pretty sure that it won't work, but let's see. Yeah, you know what, I need to use mine. Yeah, this is a problem. Yeah, because the program will now generate my own PC name and username. So I have, in order for the decryption to work, I need to use my info, not the real ones, just to understand what happens, just to figure out what this NP does. So I think that's good to go. No, we also need 08. Yeah, it was 8 in the morning, I think, when I solved this. Okay, so now we have to put 01, I believe, and peanut. Yeah. I'm afraid that it's not possible. I need to do this like that, unfortunately. Yeah. Yeah, let me copy paste this exactly as is. trust me, there is literally no reason to spend time in reversing this. It's something you can figure out quite easily. It's just I need to spend now some time and understand the right order how to send the data. The data is not required to do this right now. You can figure this out with not so much pain. It's quite doable. Okay, so this is the global. Alright, so let's take this and paste. Alright, and that, and I think we're good to go. Okay. Shit. Okay, what's that? Okay. Okay. I think that's good. Good enough. Okay, the server is running. Let's go and run it. The ISS key is constructed. Let's actually run this for quite a while. Let's see what we get. Key is not defined. Of course, it's not defined. Of course. Let's run. No, we don't want to breakpoint here. Okay, it worked. It worked. It worked. Nice. No breakpoint. Okay, probably we need to receive, to breakpoint at receive. Right? Yeah, what data are received here? Please help. This is the response. Oh, okay. No, we need yeah, we need this one. So let's rerun this. Okay, okay. What? Sure, what? Extract, not extract, fetch JSON key. Was it like that? Let's put it. No, let's remove the breakpoint from here. What? ACK. Ah, okay. What? Out of range? Ah. Oh shit, yeah, we need to rerun the server. Of course. Okay. So yeah. Okay. That's quite good. RDX. It's D. Okay, it gets D. ACK. D again. STA. Perfect. So it gets the value of OK. Then it's it's D again, but now it's just, it will be just no op. Okay, now it's message. Yeah, it gets no op, nothing to worry about. So we run again, and now, yeah, we're inside. Yeah, so now it's D, so it decrypts and it gets the message. So it's a command. Okay, so we need to step out of this and get in here. Okay, so it gets the JSON. So this should be JSON get JSON get value as well. Anyway, this should be get key value, I think, because it just fetched the value CMD from a message key, from the message key. Anyway, let's move on. So okay, this function probably determines the actual command. So let's take this and search through the entire thing. Of course, it exists in multiple places. Let's take the references. Yeah, this is it. So let's put a breakpoint here, a hardware breakpoint, just to be sure. Okay, let's debug a bit, but I'm not sure what. Oh, useless. Another useless function, just like the most of them. Okay, so it's a message, memcopy, cmd. Perfect. F9. Shit, I missed it. What's happening? It crashed. Pause. What the fuck happened? Ah. Okay, let's run this again. That breakpoint was very cool. So it's DACK, STA. It's D message. Let's try again. Okay, it's D. Okay, so yeah, it should message again. Fuck. What's happening? Isn't this another JSON? Where is the command? Oh, fuck, here you are. It's empty. D. Oh, this is no shit. Let's run this again. How am I going to see that? Yeah. Let me open this in the other screen and stop punishing myself like that. Why it lags so much? It should be instant. What? Jesus. Okay. So it takes D. It's a first D. It takes message. It's a command. Up. I don't get this. Why it takes so much time? Ah, nice. Okay, this is it. Oh no, this is not it. Oh. Let's run this again. Okay. It receives. Okay. Awesome. It receives STA. Okay. Okay. It lags so much. I hate that. I hate it. Fuck. Okay, just take the message. Cool. Okay. So here is where it receives. Here you are. Here is where it receives the important command that we need to understand what it does. So let's go step by step and see how is the response exactly handled. Actually no, let's run this one more time just to get the fetch JSON key. Oh, perfect. Boom, 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 boom. So D. Is any of them the IS decrypt method? What's the No, it's not decrypted yet. Oh wait, it decrypted? No, it's wrong. Okay. What's this method? What's this? 6C680. Oh, 6C 6, not here you are. So we are at 4D36. Next one is at 5775F5. Here you are. Let's put the breakpoint here and run this. So this is Rusty. I don't know what this is. What the fuck is that? What the fuck is that? Ah, this is obfuscated, of course. Let's breakpoint. Yeah, decompiling this would take centuries, I believe. Yeah, forget it. Anyway, let's keep this for now. My god. Anyway, so it fetches message. The message is cmd. Okay, so C5F0. Ένα 450. Μια C. Σαράντα πέντε μηδέν εννιά. Εφτά F7. 4509. Are you fucking kidding me? What the fuck is this? Oh my. Close, stop, just stop this. Not now. Come on. Fucking stupid trash. Fuck off. Actually, can. Fuck shit. Please tell me that. Oh my. Oh my god, nothing was saved. Fuck. Oh my. Who gives this? Bro, it's 3 AM. Why now? Why? Oh. Let's rebase again. Nah. What's this? Oh, nice, it's already decrypted. Fuck this shit. I missed that. Let's put one breakpoint here and one breakpoint here. And let this fucking shit run. How is it possible? How? Oh. It stopped? Amazing. What the heck? Fuck this. No. Let's run again. Okay, the rebasing is over. So the server runs. Let's run this. Not receive. No. Okay. Fetch JSON key. Is this D? Okay. So let's remove this. Okay. And what's that? Okay. ACK. Extract JSON value. No. I don't think this is actually extract JSON string, but anyway, it's too late right now. Extract JSON int value. Let's breakpoint here as well. Okay, this is RDX. Yeah, this is okay. STA. Okay. Extract JSON value. Okay, this makes sense. Let's go to the next. It's STA. So what? What the fuck, man? Let's rerun this. don't give a fuck. Let's do it. I want STA. Okay, so having STA, we need to see which method receives OK. Okay, we need a breakpoint here. Extract JSON value D. Okay, so we need this. We certainly need this. Okay, next. No op. Is this D? So it receives D. It extracts the encrypted thing. Perfect, makes sense. Message. Okay. So it receives no op. Why? Okay, this is D. It extracts ciphertext. Okay. Okay. Makes sense. It gets message. Okay. Extract JSON value 3. Okay. Oh, here you are. So so this extracts the value 6. This is the command ID. Oh fuck yeah. So this gets the command ID. Thank God. We eventually did it. Too annoying. Okay, let's move on. Fuck. Okay, next. So where is this code from? Okay, so let's run until return. The value is 14 in hex, 20 in decimal. This aligns with that. We proceed and it's over. What about fucking NP? What about fucking NP? I'm getting hysterical right now. Yeah, it crashed, yeah. Okay, let's go. Okay, it's no op. Yeah. CMD. Fetch JSON key, of course, it's D. Then it's encrypted command. Yeah, fetch JSON key. The next one will be CMD. Yeah. Oh no. Get command ID. Okay, let's step by step analyze this, because I'm not really sure that I'm staying sane for a while. Okay, we cannot skip this, we need to analyze this. So no, let's get here and check which function is it. So it's F77960 F77. So it's basically this. Yeah, okay. Oh, this is large. This is enormous. 20C90. Okay, so the next one is here. Okay. Get JSON key from command, something like that. Okay, it returns DT, of course. It extracts the value. Okay. Tac. Awesome. So the next one is sleep. It sleeps for some time. It sleeps for 20 seconds. Oh, that's why. Oh fuck. Lol. Oh shit. So it sleeps for that many. Okay, we don't want sleep. Fuck this. Forget sleeping. Oh no, sleep is on the second argument. Okay, we need to wait. So DT is how many seconds it should sleep. 20 seconds. No, we don't want this. We want 0 seconds. Okay, 1 second. Okay, we'll just wait, I guess. Wait, if I put a breakpoint here and run this, yeah, fuck yeah. So the next one is this address. Okay, we're getting there. Okay, so now we get the boss at Thundernode. Fuck yeah, this is NP. Okay, so the next one is the EFA. So the next one is at this address. Wait, what? Okay, all right. So this is a function having Rusty and the boss at Thundernode. Let's run this. And what's this function? 7f times. Here you are. Okay, so this is essentially just this function. Okay, this function expects 3 arguments: peanut, the boss at Thundernode, and rbx. What is this function? Okay, here I can I have a suspicion that the boss at Thundernode actually overwrites peanut and is used as the new identifier. But let's debug this a bit more and make sure. Let's make sure. Too many stuff, too much stuff going on. Yeah, we don't need any of this. Okay, this returns. What's that? Oh, so yeah, let's get back to this, and I think this function is over. Okay, there is still this rusty string around. So right now anyway, it's getting really late, so no, compute construct, not, yeah, so yeah, fetch JSON key is called who am I. Okay, let's go ahead and okay, fetch this ciphertext. Okay, so what's this method? Fast moves, no time for thinking. Let's go. C680, okay, let's go. This is it, 4D36. As you can see, it's very hard to keep track of what's happening in this video. I think you understand. Okay, it extracts the ciphertext. Okay, so it extracts the ciphertext and converts to bytes. Okay, so let's put a breakpoint. Let's put a hardware breakpoint until this byte is accessed. Okay, and we run, and it breakpoints at this function, and voila, check this out. The AES key is constructed again, and remember that the first time the SHA-256 hash was calculated, it used the username and the PC name, and in the second time it used peanut and 00, but this time look at this, it's the boss at Thunder node and 01 the time that is. So the NP key basically overwrites the identifier, and from peanut it becomes the boss at Thunder node. So all we have to do is go here, compute the new identifier, which is the boss at Thunder node, and decrypt the rest encrypted messages. Now take a look at this. What? What? It did not work? Why? Oh my god, identifier, fucking shit. Okay, it worked. It fucking worked. Okay. Let's go. So, yeah, this is where the identifier changed. I think NP is something like new PC, I don't know, but I call it identifier. because the user isn't something else. So the commands continue. It's another dir with a lot of stuff, and you can see a zip over here. So it no, actually, wait, it's another. Yeah, you can see this zip. It's rockandroll.zip, and the user tries to access this zip, and here the identifier changes again to Miami. Jesus. So it's Miami now, and yeah, so let's go ahead and see how many messages were left. Let's go to the last one and start from the beginning. Okay, I don't think it's actually used. Let me tell you what I mean. So it dirs, okay, it just dirs. Let me check, wait. So this is the big thing, is that's dir over there. Okay, this is no op. This is this one. This is the response. Okay, and this is this one, and this is that one. Okay. Yeah, we must be careful here not to be off-synced. It could be destructive at this point. Okay, so we need to, okay, 66. We not want this. This is no op, this is no op, and this is okay. This is this line, then it changed to Miami, so the rest traffic. So for example, this enc messages, it's the rest. I don't have any idea. Okay, this looks like a no op, so this would be useless. I don't copy it again, fuck off. Okay, this looks useless. Fuck, let's copy it as well. 79881. Okay, so this is it, and let's decrypt the rest. Okay, so the identifier changed to Miami, and then they tried to download or access, I don't know, the passwords.txt file, which is base64 encoded, and let's check this out. So this is base64 encoded. So from the file name we understand that it's a file with a text file with passwords. So the bank password is this, and the password for the rest files is that. So we expect the password of the zip file, we assume that the zip file will be protected, so it will be the password will be this password. So let's go ahead and grab the encrypted zip, which is this one. Okay, so let's go ahead and open encrypt.txt. Okay, we want to read eval bytes from hex. Is that true? No, eval is not needed. Encrypt. Let's print this out. Okay. Yeah, okay, no, not the entire thing. Just stop this. Is it still recording? Okay. Everything is lagging right now. Okay, this looks like compressed. Does not look like a zip file, so I guess it's compressed. Let's check this out. Compression. Okay, well, let's just try all the from hex. So it's not gunzip. Let's try inflate. Zlib. Why is it lagging so much? Fucking god. Okay, zlib. No, zlib inflate. No. No. Is it anyway? I don't have any idea. So I'm going to cheat here a bit and yeah, no way. Yeah, what's that? Probably. No. Magic bytes. No. 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 What do I miss? Who cares? Let's stop this up. Wait. Okay. Oh, wait. Am I dumb? Wait, oh my god. I need to convert from base 64. Okay. Being alive at this moment is itself amazing, so I can forgive myself. Okay, let's print this out. Okay, we don't need this anymore. Let's close this fucking IDA also. And it does not work. Why? What is inside encrypt? So it's encrypt.txt. Okay. No. Of course this not work. What did I miss? Please help. Just okay. It turns out that okay, one can figure it out with further reversing. I will not do it right now, I'm exhausted. So yeah, take my word for this, and yeah, take my word for this, and this is fucking disgusting. This really did not work. Fuck! Thunder node! Okay, fuck this shit. Okay, this works. So we load this as a JSON and we access the FC and we base 64 decode it. Okay, and the zip now should look like that. What? fuck my life eventually. We got, so let's write the basic 64 decoded zip. This is the basic 64 encoded zip, and it's over. What? No, wrong. This is it. Yeah. Extract. The password is, what was it? This is it. And look, for this part with the FC, we could just go to the we would just simply keep on debugging and breakpoint at the handler for the FC command, and then just figure out that it re-encrypts the entire thing, right? Yeah, and eventually you would figure this out with a few more trial and error. So yeah, this was 6 hours. It's insane. It's my largest video I've ever done, and probably the largest that I will ever do in this channel. I don't think there will be any other case that one should take so much time for a video. I even can't speak right now, but I really don't think that there will be any other motive to make such a lengthy video again in the future. Maybe for 8, but number 8 will certainly not take so much time. Yeah. So yeah, this is the flag, the challenge. That was my solution process, more or less. Yeah, actually, I think my approach today was kinda accurate, and almost about 90% accurate as to how I actually solved it while I was solving this. But it did not take me 6 hours. It took me much more, because I was troubleshooting the good request decryption. I was troubleshooting the identifier modification. I was having much more trouble, but I was about 90% accurate, and I am pretty proud of that. Anyway, so if anyone is still here after so much time, respect. I hope you found something useful from all of this, but mostly it was just me burning my head over x64dbg. I did not even spend a minute deobfuscating this entire mess in IDA. It actually crashed my IDA client twice. Yeah, I did not even bother. Anyway, that's all from me. Hope you enjoyed this video, and see you on the next two. 2 left. Bye.